before I kick on then with anybody, can everybody see the screen okay? Is the first thing.
Yes, we can see.
Yeah, lovely. And then we'll have a bash with the film in a little while, and we'll see if we can get that to run. What I would say is it's an old film, but it does explain things quite well. I'm well aware that there's only a couple of questions come from high speed flight, but again, I'm duty bound to go through it, and anything that I recognise from previous exams, again, I'll tip you the wink first, stick your highlighter through it. But before I carry on with any of that, has anybody got any questions on anything that we covered yesterday? Nope, super duper. Right, in that case, we'll push on, and this morning we're going to have a wee look at high-speed flight, what goes on there. One of the things we talk about is shock waves. Yeah, and I don't know whether you can see the shimmer under the aircraft there, and that is an example, one of the few examples you get of a visible shock wave. So that's why the illustrations there. So what we're going to say about high-speed flight then. Yeah, high-speed flight, our aircraft, we've done the basic aerodynamics. We know what the lift formula is, and we know how the airflow is passing over the aerofoil, yeah, and how we're generating that lift. We've looked at angle of attack. We know about wing shape. Obviously, the density of the air and the speed of the aircraft are going to have quite an effect on our lift. Yeah. So lift formula, as we go snotting through the air, there are going to be various changes to the density of the air and the speed of the aircraft that is going to have an effect. Yeah. When any object is moving, be it an aircraft, be it me talking to you, be it me scratching my head, when any object moves at all, it sends out little pressure waves all around it. And those little pressure waves travel at the speed of sound. Yeah. With our airflow, the air streams in front of the aircraft, because of these little pressure waves that are being generated, the air streams in front of the aeroplane get an idea that something's coming towards them, so that the streamlines can adjust, they can open slightly to allow the smooth passage of whatever is traveling through the air. These little pressure pulses, yeah, they travel at the speed of sound, yeah, which is about 760 miles an hour in the air at sea level at 15 degrees. Yabba dabba do. Yeah. The air in front of the object, yeah, so we've got our aerofoil. The aerofoil traveling nice and slowly, we're going to get these little pressure waves moving out in front of it. So the streamlines in front of the aerofoil can open slightly and allow for smooth passage. Yeah. Anything that happens at the aerofoil, yeah, again, any slight movement is sending out these pressure waves. So again, the airflow is going to separate, and again, it gets a warning of the approach of an aerofoil coming towards it. So it'll separate slightly, and again, that gives for a nice smooth passage. If the air is traveling at low speeds, yeah, the airflow passes over the cambered wing. It accelerates It goes faster as it flows over the wing, but it doesn't undergo any changes. Yeah. The air in front, as we said, gets its advance warning due to the pressure waves moving ahead of the aerofoil, and those pressure waves moving up at the speed of sound. So let's say the aircraft's chugging along there quite happily, way below the speed of sound, so that the streamlines in front of the aerofoil can open up slightly, if you like, to allow smooth passage. The air flowing over the top of the wing accelerates as it goes over the point of camber, maximum camber, passes along slowly, and then trogs off on its merry way. Problem that we get, is as we start to accelerate the aircraft. So the pressure disturbances that we talked about, traveling out from we'll say the nose of the aircraft, whacking forward, and the streamlines in front are getting a warning that there's something coming, so that they can open up slightly. The problem we've got, if we've got an object traveling to from point A to point B, the pressure waves transmitting in front of the object, they're not causing any major problem. But if the aircraft starts going faster and faster and faster, because the pressure waves are traveling at the speed of sound, the aircraft's traveling at the speed of sound, those pressure waves can't escape forward, so that the air in front of the aeroplane has absolutely no indication that the aerofoil is approaching. It can't open up, it can't get out of the way quickly enough. And what happens is we end up getting a pile up of those waves. They start to pile up because they can't get out from in front of the aircraft fast enough. So again, just to try and sort of explain that, the aircraft traveling slowly or below the speed of sound, the pressure waves transmitting out in front of it, there's no interference. As the aircraft builds up and it gets to the speed of sound now, the pressure waves are transmitting forward as fast as the aircraft's going, so that they can't escape quickly. They're not flying in front of it or not moving in front of the aircraft quick enough, so that they start to build up, they start to pile up. And that is what forms the shock wave that we're going to talk about. Once we are flying faster than the speed of sound, the shock wave has moved over the aircraft. It starts moving back over the aeroplane, and once we've gone through that stage of the shock wave forming, the aircraft flying faster than the pressure waves, so the pressure waves are going to move to the tail of their aircraft, and they're not going to have much of a detrimental effect. So that the pressure waves now trailing out behind the aeroplane. The air outside that shock wave is totally unaffected. So we have the three sort of regions that we're looking at. We have the subsonic, where nothing's happening. We have a transonic region where we're flying up to and just past the speed of sound, and then we've got the supersonic region where we're beyond the speed of sound, if you like. So we'll kind of wander on, and we'll have a look at that. Again, just nipping back to the notes, it says at low speeds, when the airflow passes over a cambered wing, it accelerates, but the air is not compressed. Air receives advanced warning due to the pressure waves moving ahead of the body. But as the speed of sound is approached, there's less opportunity for that air to be accelerated, and it becomes compressed. Then it just goes through to show how the pressure waves move out. And again, when I show you the wee film in a few minutes, hopefully that will amplify and clarify what I'm trying to say. It's quite a difficult one to express. Yeah, so object traveling from A to B, yeah. As it's below speed, yeah, there's the ripples, bit like throwing a pebble in a pond. The ripples will just travel out for all directions, yeah, uniformly at the speed of sound. But if object A's are not moving, the ripples will just carry on till they run out of energy. If now I start my object moving, yeah, it's starting to catch up with the ripples that it's generating, and as it generates those ripples, eventually it's going to catch them up, and they're all going to pile up on one another, and that's where our shockwave forms. Yeah, one of the most important things that we need on our high-speed aircraft is to know how fast the aircraft is traveling. The speed of sound varies with the temperature of the air in the locale, and because the speed of sound varies with temperature, yeah, obviously the speed of sound is going to be different at different altitudes. Because it's the speed of sound that is affecting the point at which the pressure wave is going to form on the aeroplane. What we need to know is, and it's going to structurally affect the aeroplane and the flying characteristics. So what we need to know is where that pressure wave is going to, when it's going to form. So what they came up with was a thing called the Mach number, and the Mach number is the ratio of the true speed of the aircraft to the speed of sound locally. Yeah, the concept of the Mach number, as it says, very, very useful because the aerodynamic effects around and above the speed of sound depend on Mach number rather than the actual speed of the aircraft. Because the speed of sound varies with temperature, yeah, the stratosphere, the temperature of the air, as it said, about -60. So the speed of sound in the stratosphere is about 660 miles an hour. Down at sea level, where the temperature is a lot warmer, about 15 degrees, the speed of sound is going to be about 760 miles per hour. So if the aircraft's flying at high speeds, the pilot needs to know the speed of the aircraft in relation to the speed of sound, and that's where the Mach number comes in. Yeah, so your Mach number, the true speed of the aircraft by the speed of sound locally, it's a ratio between the two, and that at the top of page 72 is again well worth sticking a highlighter through. The Mach number, the ratio of the true speed of the aircraft to the speed of sound locally. Again, stick your highlighter through the fact that the Mach number, or the speed of sound, varies with temperature. Sorry, it's the speed of sound that is varying with the air temperature. Yeah, so true speed of the aircraft, if you're flying at 760 miles an hour, yeah, speed of sound locally down at sea level, 760 miles an hour, we're looking at a speed of Mach 1. If I'm flying at 380 miles an hour at sea level, that's 15 degrees C. Yeah, your 380 divided by your 760 brings you 0.5. So the aircraft would be flying at 0.5 Mach. Yeah. If I go up to altitude, if I'm up in the stratosphere, you're 380 miles an hour at -60 at 40,000 feet. Yeah, your 380 divided by your 660, we're looking at 0.58 Mach. Yeah, it may well be that your aircraft is limited structurally to how fast it can be flying. So in this case, the aircraft's limited to 0.8 Mach. 0.8 by 760, 610 miles an hour. 0.8 by 660, 530 miles an hour. So that the altitude, as we gain altitude, the maximum speed of the aircraft needs to be reduced to keep it within its limits. Yeah, so the Mach number, very, very useful. Yeah, so the crew can look at the Mach meter. That Mach meter is going to say, right, well, your aircraft's limited to 0.8 Mach, and that's going to let you know what the maximum speed is for particular altitude that you're flying at. Anything else we need to know there? Yeah, aircraft flying at the speed of sound, the Mach number will be considered as Mach 1. Anything around that will either go up or down accordingly. Yeah, aircraft flies through the air. Yeah, we've said that every part of the aircraft is producing these tiny little pressure waves, these pressure disturbances, and they radiate outwards from the aerofoil and, well, indeed the aircraft, but we're sort of concentrate on the aerofoil. Disturbances are going to radiate outwards in all directions, and they're going to radiate out at the speed of sound. In subsonic flight, yeah, disturbances or waves travel forward faster than the approaching airflow. So the approaching airflow gets a warning that something's coming. The air flows over the wing, it accelerates, but that air, the aircraft's moving where it says here 0.6 Mach, subsonic flow coming in front. The air's going to flow over the aerofoil, around the aerofoil, and it's going to travel at subsonic speed. Yeah, we'll get the separation point that we've already discussed. So here, everything nice and happy. So the airflow hitting the nose of the aerofoil. Yeah, you get your, what was it, the stagnation point, then the airflow will move around the aerofoil, but it's moving subsonically. So everything's quite sweet, quite happy. Yeah, as we increase the Mach number, the airflow over the wing, yeah, is going to accelerate. Yeah, the wing's moving faster. We're going into subsonic flow, but the flow over the wing is going to be accelerated by the camber of the wing. As it flows over the top of the wing, yeah, the pressure waves that are being radiated from the aerofoil are trying to move forward. The airflow moving over the top of the wing is moving backwards quicker than the pressure waves can move forward. So what happens is they start piling up together. As the airflow is accelerated over the top of the camber, it's going to get to a point where it's actually reaching the speed of sound. So although the aircraft is hitting subsonic flow, that airflow is being accelerated over the aerofoil. It is going to reach Mach 1. It's going to reach the speed of sound. As it reaches the speed of sound, obviously the pressure waves coming forward, the air flowing backwards, they're going to meet each other, and that is going to form a shock wave on the aircraft. So as the two meet together, they're forming this, it's a kind of barrier, and the shock wave is going to fall up, start to form on top of the wing. So from the point of maximum camber, the airflow reaching its supersonic speed, its Mach 1 speed, yeah, airflow coming the other way, can't get out of the way quick enough. This shock wave builds up, and that shock wave builds up at 90 degrees to the aerofoil, and that shock wave is known as a normal or an incipient shock wave. The point at which the airflow accelerates to the speed of sound over the aerofoil is known as the critical Mach number. Yeah, the aircraft is traveling at its critical Mach number. Excuse me, young lady. Yeah, very pretty. Right, got to keep an old man happy, haven't you? Yeah, so the normal shockwaves formed. As the air tries to force its way through that shockwave, it's going to go through a big change. The temperature of the air behind the shockwave is going to rise dramatically. The pressure's going to increase and the density is going to increase. So what happens is behind the shockwave, yeah, we get an awful lot of the air slows down very, very quickly as well. Yeah. And because of those effects, what happens is we get an awful lot of turbulence behind the shockwave. And because you've got all that turbulent air behind the shockwave, that's going to cause the aircraft to quite possibly stall. Goes into what they call the shock stall. That stall wave, yeah, can form, the shockwave forms when the aircraft's moving around about 3/4 of the speed of sound. Yeah, the aircraft is moving at let's say 0.75 Mach, but the speed of the airflow, the aerofoil, speeded up, and that will reach the critical Mach number, the speed of sound over the wing. Yeah. Pardon me. Yeah. So when we get to the shockwave forms. Behind the shockwave, there's sudden rise in pressure, density, and temperature of the air. The airflow is slowed down by the shockwave. So behind there, the boundary layer breaks away and becomes very turbulent. A lot of buffeting on the aircraft, rapid rise in drag, consequently loss of lift, and it does say that the centre of pressure will move rearwards as well. Loss of effect of the control surfaces because they're working in what is effectively dead air, and that buffeting because of all the turbulence. If the tailplane's in the way of that turbulent air, again, that's going to start throwing the aeroplane all over the place. So with an increase in Mach number, the shockwave grows in intensity, and the faster we go, that shockwave starts to move backwards. Yeah. As that shockwave moves backwards, a greater portion of the upper surface covered with supersonic flow. I'll show you a picture of that in a moment. Airflow passes through the shockwave, and then we get all those different effects. Yeah, so aircraft goes flying. Yeah, pressure waves, pressure waves, pressure waves. Air coming forward, we start to get this shockwave forming. Shockwave builds up on the aerofoil, and the faster we go, we'll start to get a smaller shockwave forming on the lower surface. The faster the aircraft travels, that shockwave will start to move to the rear of the aerofoil, and the one on the lower surface, the faster we go, start to move as well. This picture, you can see we've got a shockwave already formed, but you can see behind the leading shockwave all that turbulent air, and you can see all the separation of the air from the aerofoil. As that shockwave moves back, yeah, that disturbed air is going to move back as well. So the faster we go, once we go into supersonic flight, that shockwave is going to move back, and the effects of the shock are going to be reduced over the aerofoil. Again, similar to the picture that I showed you earlier, we can start to see it's been captured. Hopefully, you'll be able to see the shimmering at the back of the aeroplane, and just on the top of the canopy there, you can see the shimmering there. Hello?
Sir, can a shockwave will form both sides of airfoil, sir?
Yes. Yes, because it's the speed of the air that's flowing around the aerofoil. Don't forget with your aerofoil shape, yeah, you've got more curvature over the top than you have on the bottom. So as the airflow moves over the top of the aerofoil, it's going to accelerate. Yeah, because that airflow as it's flowing around is accelerating, it's going to reach the speed of sound at the point of maximum camber. The air that's traveling under the lower surface, yeah, is moving slower than the air on the top. So the shock wave on the lower surface is going to form at a later point because it's not getting that acceleration as it goes over the point of maximum camber. Yeah. Okay. So as the aircraft goes faster and faster, the top shock wave will start to move backwards, and you'll get a smaller shock wave forming on the lower surface.
Okay, so means upper side it will be higher than the lower one, so, right? Yeah,
it tends to be until they reach the rear of the aerofoil, which we'll come on to in a minute.
Okay, so good.
Yeah. We're talking about curved surfaces, and again, we focus on the wing of the aeroplane. We look at the aerofoil, but the faster the aircraft's going, wherever we've got any curvature where that airflow is going to be accelerated, shock waves can form, and hopefully just on top of the canopy there, you can see that there's a shock wave forming. So as the air's accelerating over the top of the canopy, yeah, it's forming a shock wave there. Yeah, so that these things can form at various points on the airframe, although we consider the aerofoil because that's the logical place to look. Yeah, so as the aircraft's flying along, yeah, it's in the subsonic region, but the air that's flowing over the wing is going to accelerate, and that air is going to get to the speed of sound locally. Where that happens, that is the critical Mach number. We're looking in the supersonic region. Yeah, if we carry on accelerating the aircraft, then as we go through the transonic area, the drag is going to increase because of the effects of the air trying to get through that shock wave. And then as we come out of the transonic region into the supersonic region, the effects of that drag are going to reduce dramatically. Yeah, again, we'll have a look at that in just a moment. Yeah. What's that? No, that's 10 o'clock. I'll just do this bit, and then we'll have a cup of tea, and then I'll stick the wee film on, and hopefully that will clarify everything that I've tried to say. But is everybody okay at the minute? Has anybody got any questions so far? Oh, lovely. Right, so shockwaves forming. Yeah, just an example from the wind tunnel. It's showing the shockwaves forming, and the faster the aircraft's flowing, the shockwaves are going to move back along the aircraft, along the aerofoil. But the faster it goes, a second shockwave is going to start building up, and that's where we're looking at going into supersonic flight. Yeah, so yeah, aerofoil traveling at let's say 0.8 Mach here. Subsonic flow in front. Yeah, that subsonic flow as it strikes the aerofoil, yeah, it's still going to be subsonic, and then as it moves across the aerofoil, it's going to start to build up the shockwave. The faster we go, that shockwave is going to move towards the back of the aerofoil. So now the airflow across the front of the aerofoil is supersonic. So we've got a mixture of supersonic flow, and then the air behind the shockwave slowed down dramatically. We get all that separation, all that turbulent flow behind. The lower surface of the wing, the airflow accelerating, but at a slower rate. Yeah, but eventually we're going to get supersonic air on the low surface, and we're going to get a shockwave forming on the low surface as well. Behind that shockwave, the same effects. We're going to get subsonic flow. Carry on going faster and faster. Yeah, the air in front of the aerofoil is subsonic, but as we're approaching Mach 1, yeah, now the airflow over the whole aerofoil is supersonic, moving faster than the speed of sound. Yeah, the shockwave moves right to the very back of the aerofoil. So now the separated air, yeah, is behind the aerofoil. Yeah, so the two shockwaves will travel along to the trailing edge, where they'll attach themselves there. Yeah, and then we get to the point where the normal shockwave has travelled to the tail of the aeroplane. The aircraft is flying supersonically, so the air that it's meeting is supersonic. Yeah, just as it's meeting the aerofoil, it slows down. Region of subsonic airflow in front of the aerofoil. But what you see now is we get another shockwave starting to form. Yeah, the rest of the airflow over the aerofoil is at supersonic speed. So what we end up with is three sort of distinct regions where the flow of the airflow across the aircraft is either all subsonic, which is what we call subsonic region, and that is at speeds below 0.8 Mach. The transonic region is where the airflow is at mixed speeds over the aircraft, as we said, some supersonic, some subsonic. And your transonic region is 0.8 to 1.2 Mach. The supersonic region is anything above 1.2 Mach, and all the airflow of the aircraft now is at supersonic speed. Yeah, so the shock stall, the turbulent airflow behind the shockwave causing that severe buffeting, is often referred to as the shock stall. It's not like a normal low-speed shock stall because it occurs at smaller angles of attack. It's the flow of air over the wing that's being destroyed, rather than the aircraft angle of attack getting to the point where the air can't flow over it. The speed at which the shock stall occurs depends on the aircraft type. Yeah, fair enough. But it's always less than Mach 1, and it's always referred to as the critical Mach number, or the shortened version M-crit. Yeah. So what we want to do is to try and raise that critical Mach number for the aerofoil, so that the higher the M-crit number, the better. Mach number increases, yeah, as the aircraft's going faster, yeah, and that we now get that mixed region of airflow. Mach number approaches the speed of sound. The area of supersonic flow, as we said, continues to grow over the aerofoil, and the shock waves increase in intensity. They move rearwards to the back of the aerofoil. Yeah, once we're covered in our supersonic flow, yeah, apart from the wee bit at the front, get above the speed of sound, we're going to get another shockwave in front of the wing, and that's known as the bow wave. The original shocks to the trailing edge. Aerofoil covered in supersonic flow, airflow fully supersonic, fully developed, bow and tail waves attach themselves. So the faster the aircraft goes, that bow wave will eventually, just click back here a bit, that bow wave that forms will eventually attach itself to the leading edge of the aerofoil. Yeah, it'll start off fairly square, but the faster we go, yeah, that bow wave will start to attach itself. So now everything behind that bow wave is going to be supersonic. The whole aerofoil is going to be covered in, what's happened? In supersonic air. Yeah, so down to page 76, at the bottom of page 76, yeah, the subsonic region of flight, the range of speeds below 0.8 Mach. Subsonic speeds, the airflow over all of the aircraft is subsonic. Transonic region, 0.8 to 1.2 Mach. Transonic speeds, we've got a mixture of airflow. Some of it is subsonic, some of it is supersonic. Supersonic region is anything above Mach 1.2, and at supersonic speeds, all the airflow over the aircraft is supersonic. Everybody okay with that? And again, those figures, those regions and the speeds associated with those regions, again, you'll need to highlight those. Yeah, so most of our aircraft, our large aircraft, are going to fly in the transonic region. Yeah. So what we need to try and do, not so much as the engineer, but certainly as designers, what they want to do is to raise the critical Mach number as much as they possibly can. So we're keeping the airflow over the aircraft nice and smooth, and we're reducing the strength of the shockwave that's going to form. Yeah, so increasing the Mach number, we're delaying the onset of that shockwave, and by delaying the onset of the shockwave, we're reducing the intensity and the effects of the shockwave. Some of the methods they can use, again, just to show you the shockwave forming, that was on a wee missile. Yeah, it gets shockwave, travels back. You can see that one's attached itself to the rear of the aircraft, and there's another one attached at the front. Yeah, forming a bow wave and a tail wave. Don't worry about the bits in the middle. We're not going to over confuse things. This was thrust, the land speed record car, and there's that fight across the desert in the salt flats. Yeah, again, as it got the speed of sound, you can see the shockwave forming in front of it, and that's quite a good example of a shockwave. So what we're trying to do is to raise the critical Mach number. Yeah. And one of the methods they can use is slimness. Yeah, making the aerofoil sections, the fuselage, the engine nacelles, making those as slim as possible, and that makes sure that the airflow isn't accelerated locally, so we're not getting shockwaves forming. Yeah, the ideal aerofoil sections would have a low thickness to chord ratio. The lower they can get it, the better. So that's one method of increasing the Mach number. Another method they can use is sweep back. Yeah, so if we sweep the wings and the tail back, the shock stall, the M crit is increased. Sweep back reducing the intensity of the shockwave when it does form. It goes into the maths about it. The component of the airflow velocity across the wing chord forms the shockwave. Wings swept back. If you think about it, that chord length, yeah, with a normal or slight sweep back, yeah, the chord length of the wing quite straight. If we sweep the wing back, yeah, what we're doing is increasing the effective chord length. Yeah, So now the air has got further to travel before the shockwave can form. So that the example it gives there, the angle of sweep back 15 degrees, the velocity of the air going across the chord, yeah, it says v cos theta. I'm not a mathematician. I'm not going to do that. But if we're traveling at 600 miles an hour, yeah, obviously that v cos 600 times 0.966, whatever that is, and that works out to a limit of 580 miles an hour. If we sweep the wing back, we increase the angle of sweep back, same velocity for the aircraft, but now we've reduced the velocity. So now the airflow is traveling at a much reduced speed over the wing because we've increased that effective chord length. As I say, I apologize, I'm not a mathematician, but it does work. You can do it with a piece of folded paper, yeah, and a ruler. You can make your own. Just put a piece of paper down, put a ruler on a square level, draw the length of the chord, move that chord to an angle on your piece of paper, and then draw your line again, and you can see that the chord length does increase as you sweep the wing back. So by sweeping the wings, yeah, we're lengthening the chord effectively. The wing thickness isn't going to change. We're not doing anything with that. Yeah, by reducing the chordwise component, yeah, we're increasing the critical Mach number. Yeah. The only downside of that is you reduce the lift that's being produced by the wing, but sweep back does work. Another method that the designers have come up with is by inventing what they call a supercritical wing. The supercritical wing is a design where the curvature of the aerofoil accelerates the airflow over its upper surface to more than the speed of sound, but the smooth, we've reduced the camber on the aerofoil. Yeah, so with your conventional aerofoil, we get that incipient shockwave forming. It's very, very strong, yeah, because the aircraft or the airflow is being accelerated quite a lot. With the supercritical aerofoil, we haven't got that level of camber over the top, so that the shockwave that forms tends to form later, and it tends to be a lot weaker. Yeah, so most airliners cruising at 0.7, 0.85 Mach. I'm just reading off the notes here. At high altitude, at those speeds, the curvature of the airfoil accelerates the airflow over its upper surface to more than the speed of sound. Airflow over that upper surface is now said to be supercritical, and that produces your shockwave. Yeah, supercritical, just saying that the airflow is past that Mach 1. Airfoils travelling at speeds lower than Mach 1 are called subcritical. Speeds faster than Mach 1, supercritical. So the supercritical aerofoil has a relatively flat upper surface. Supersonic airflow stopped by one or more weak shock waves instead of a single strong one. So it'll form a number of small weak shock waves. More lift produced at the forward part of the wing. So that allows, it says, smaller wings to be used on the aircraft. The wing can be deeper, thicker, so we can use it for tucking up the undercarriage, and because it's smaller, it reduces weight, drag, all that sort of thing. So the supercritical wing is just a method of increasing the M-crit for the aircraft. So now, as the air flows across, yeah, it's going to take longer before the shockwave forms. The longer it goes on, the weaker that shockwave is going to be. So the air trying to go through that shockwave isn't going to have the same dramatic effect as it would going through a conventional shockwave. It still generates the required amount of lift, but the shaping of the wing means we can have a smaller wing, so we're saving weight there. Means we can have a deeper wing, so things like undercarriage, stowage, we can do that. And that kind of shows you the shaping of the supercritical aerofoil. That I think would be a good point to go and have a cup of tea, actually. Has anybody got any questions of that at the minute? Are we okay with that? Hopefully, when I stick the film on after tea break, it should amplify and enhance and clarify what I've been trying to say. Okay, well, yeah, if nobody's got any questions, then we'll nip off. We'll have a cup of tea at 10:15, so 10:35, 20 minutes, cup of tea, stretch your legs, stretch your eyes, and we'll regroup again, and we'll have a bit more play. Okay with that?
Okay.
Okay, right. I'll see you in a few minutes then.
Okay.
Right, are we there, guys? Everybody back? Yadav, you're my spokesman. Are you there?
Yes.
Lovely. Can you see the thing high-speed flight on your screen?
Yes, very well.
Lovely. I'll start to play it. Can you tell me if you can hear the sound?
Sure. Yeah, we can hear it.
You can hear it, right. What I'm going to do, guys, then, I'm just going to put this wee film on. Hopefully it'll explain everything that I've been trying to say, and then what I'll do up to lunchtime, we'll just have a flee through the notes, make sure that we've covered everything, and as I go through, anything I recognise, again, we'll make sure we've got it highlighted. Everybody okay with that?
Yes, Jim.
Fantastic. Right, enjoy. Like I say, it's very, very old, but it's good at explaining.
When an airplane moves forward, the air begins to flow over its wings. Once it's moving fast enough, this airflow over the wings lifts it off the ground. In flight, the airflow over the wings continues to support the airplane and keeps it up in the air, provided it's moving forward fast enough.
Can we hear that all right?
Yes, we can hear it.
As the airflow passes over the wing's curved upper surface, it speeds up temporarily and slows down again at the rear. This speeding up causes a reduction in air pressure on the wing's upper surface, and this gives the aircraft its lift. But when aircraft fly faster than about 400 miles an hour, things begin to get complicated. The speed at which sound travels through air comes into the story. This film will describe some of these complications and show why aircraft intended to fly at speeds near or above that of sound have to be designed differently from low-speed aircraft. Let's first consider how sound travels. Slowing down the picture shows how the sound is produced. The vibrating prongs give the air a succession of pushes, and like pressure waves along a spring, the sound waves travel on through the air. Sound waves are, in fact, one kind of pressure wave. Like ripples on a pond, they spread out from their source in all directions. Not all pressure waves are audible, but all small disturbances, audible or not, travel outward at the speed of sound. Watch this explosion a mile away. Its sound takes 5 seconds to reach us. At sea level, sound travels at about 760 miles an hour. But the speed depends on the temperature of the air, which drops as we climb upward. In the stratosphere, which begins at about 36,000 feet, the speed of sound is only about 660 miles an hour because of the lower temperature. Now look at the wing again. Every point on it, by traveling through the air, sets up tiny disturbances which move outward as pressure waves at the speed of sound. And parts of these disturbances reach the air ahead of the wing. Here, smoke is used to show how the air flows. Lowering a flap affects the airflow well ahead of the wing. This is because the tiny pressure waves warn the air ahead of the wing's approach. This warning allows the air to part smoothly round an aircraft, provided it's flying well below the speed of sound. At higher speeds approaching the speed of sound, the exact relation between the speed of the aircraft and the speed of sound becomes very important. It's called the Mach number, usually shortened to M.
Brush your teeth in less than 10 seconds with this revolutionary toothbrush. It was created by a well-known British dentist, and it...
This is how it is calculated. This aircraft has flown 6/10 of a mile in the time the sound wave traveled 10/10 of a mile. It has flown at 6/10 of the speed of sound in the same atmospheric conditions. That is, it has flown at Mach 0.6. This aircraft is flying at Mach 0.9. At high speeds, it's essential for the pilot to know his Mach number, and Mach meters are fitted to all high-speed aircraft. What actually happens to the air in the aircraft when approaching the speed of sound? The airflow speeds up as it passes over the wing and reaches the maximum speed at a certain point on the wing. So the Mach number of the air at this point is greater than that of the aircraft as a whole. As the aircraft's speed increases, so does the local Mach number at this point on the wing. Eventually, just at this point on the wing, the air reaches the speed of sound, although the aircraft as a whole is still flying slower than sound. The aircraft's Mach number when this happens is called its critical Mach number, usually written M crit. Soon after this, things can begin to happen. This aircraft is buffeting violently. Aircraft vary in their behavior above the critical Mach number, but until designers overcame them, there were always some adverse effects. They're caused by shock waves. Let's see what this means. If a model wing is put into a high-speed wind tunnel, a special photographic technique known as schlieren makes visible the places where the pressure of the air changes as it passes round the wing. In this picture, wherever the color is green, the speed and pressure of the air are almost constant. Blue has been chosen to show up the areas where pressure is falling fastest, while red shows where the air is being slowed down and pressure is increasing. Now look at a diagram. At the critical Mach number, the airflow is moving across the wing at this point at exactly the speed of sound, m equals 1. Above the critical Mach number, the point grows into an area in which the flow is faster than sound. M is greater than 1. Everywhere else, the flow is slower than sound. M is less than 1. The rear boundary of this area is formed by a shock wave. As the speed is increased still further, the shock wave grows larger. What causes the shock wave? Think again of the tiny pressure waves radiating out at the speed of sound from every point on the wing. The ones coming from points on the rear part of the wing, such as this one, meet airflow coming the opposite way and make less and less headway until they can't travel any further forward at all, because the airflow itself is moving backwards as fast as they are moving forward at the speed of sound. It's like trying to step off an escalator going the wrong way. The little pressure waves pile up, building into one big pressure wave, the shock wave. And here's the real thing in the wind tunnel. The wing has just passed its critical Mach number, and there's the shock wave, red because it's a sudden, sharp increase in pressure. But shock waves don't only form on wings. Wherever the air speeds up enough in its passage over the aircraft, on cockpit canopy, fuselage, and stabilizer, there too shock waves will form. The most striking effect of shock waves is a sudden, very sharp increase in the aircraft's drag. This is because the shock wave heats up the air and compresses it, And this absorbs a lot of extra energy, which has to be continuously supplied by the engines.
This new ultra-strong glue is taking over the market.
The rate at which the drag increases is itself highest somewhere around Mach 1, although the actual drag goes on growing all the time. This sudden increase in drag above the critical Mach number is what used to be meant by the sound barrier. Most of the other adverse effects of shock waves arise because they cause the airflow to separate from the wing surface. This produces a large wake of turbulent air behind the shock wave, which alters the pressure around the wing. This in turn may cause loss of lift, and some aircraft may lose height. In others, one wing may drop. The aircraft may pitch, or porpoise as it's called, or undergo other weaving movements such as snaking and Dutch roll. The turbulent airflow from behind the shock waves may hit the stabilizer or other parts of the aircraft and cause buffeting. Or the controls may be affected. Here, slowed up about 40 times, is a Schlieren picture of what may happen to an aileron as a result of shock waves. How have aircraft designers overcome these shockwave troubles? One way is to put them off to still higher speeds by actually raising the critical Mach number of an aircraft. The designer does this in two ways. First, by using relatively thin wings, wing sections whose thickness is small compared with their width from front to rear. The thinner the wing, the less the air is speeded up while traveling over it, and so the higher the critical Mach number. The second method is to sweep the wing back. Suppose this unswept wing has a critical Mach number of 0.8. If we sweep the wing back, only that part of the airflow at right angles to the wing is speeded up as it passes over the wing. So the critical Mach number is raised, in this case to 0.98. High-speed jet airliners use thin wings and sweep back to obtain high critical Mach numbers. By cruising at high speeds but still below the critical Mach number, they avoid shock waves altogether and the troubles that come with them. But wings can't be made too thin or too highly swept back, or low-speed flight and landing would suffer. And what about aircraft which have to fly much faster than sound? Designers of such aircraft have had to accept the presence of shock waves and find ways of overcoming their effects. Above the critical Mach number, speeds are grouped into two ranges. The transonic range covers speeds at which the airflow is mixed, part subsonic, part supersonic. Here, subsonic airflow is shown in dark green and supersonic in light green. Remember that wherever there are shock waves on the aircraft, there are supersonic regions in front of them. The transonic range, shown here in this wind tunnel picture, begins at the critical Mach number and extends through Mach 1, the speed of sound, to about Mach 1.3, depending on the design of the aircraft. Speeds higher than this come into the supersonic range. Here, shock waves are still present, but the airflow is now supersonic everywhere, even behind them. For transonic flight, thin wings and sweepback are again used, for by lowering the speed of the air as it passes over the wing, they reduce the severity of the shock waves. Compare the characteristics of thicker and thinner wings in the wind tunnel at the same speeds. Streamlining an aircraft's cross-section helps to reduce the huge increase in drag. The aircraft's shape is modified so that the cross-section area pushing through the air changes smoothly from nose to tail. This usually means giving the fuselage a waist to compensate for the wings and flaring it out again behind. Above Mach 1, sharp leading edges and pointed nose help to reduce the drag caused by another shock wave which appears in front, the bow wave. This is rather like a bow wave on water.
The funeral industry has been ripping off the public for more than a decade because the majority of people don't know this simple truth.
With a sharp leading edge, the bow wave attaches itself, more like this one from a motorboat. Buffeting is reduced by putting the stabilizer above the wings or below them, so that it misses the turbulent air coming from the shock waves on the wings. Control of the aircraft with shock waves is also helped by an all-moving stabilizer, instead of the normal fixed stabilizer with elevators on the end. Powered controls are also essential. Shock waves exert such huge forces on all the control surfaces that no pilot could control the aircraft manually. All these improvements in design have conquered shockwave troubles and helped to make transonic flight safe and relatively simple. In supersonic flight, the air flowing past every part of the aircraft is supersonic and behaves quite differently from subsonic airflow. Here's a section of a supersonic wing. The sudden corner on it couldn't be used on a subsonic wing, for, as the smoke shows here, subsonic airflow becomes turbulent and confused past the corner. But supersonic flow, surprisingly enough, can turn the same corner easily, as shown in this diagram. As it does so, the air expands through the region shown here in blue, and pressure is reduced. A sloping shock wave coming from the opposite kind of corner swings supersonic airflow smoothly the other way. The corner may be at the leading edge of a wing. So supersonic aircraft can use sharp corners, as for instance, the double wedge wing section. The changes of pressure caused by the shock wave and blue areas give the wing its lift. Here's a wind tunnel picture at nearly twice the speed of sound. Another shape formed by two arcs of circles is the biconvex, which, like the double wedge, has sharply pointed front and rear edges. The trouble about these wing sections is that they give very poor lift at low speeds. They can be used on missiles, such as this one, with double wedge wings. But for manned aircraft, which have to take off and land, it's not so simple, and very long runways are needed, and sometimes even extra braking devices. Today, the problem is met for most supersonic aircraft by once again sweeping the wings back at a bigger angle than for subsonic or transonic aircraft. The wings can then have a subsonic section, rounded leading edges, smooth curved surfaces, and no sharp corners. But there have been a few supersonic aircraft today with straight, unswept wings using the supersonic biconvex type of wing section. And at speeds around Mach 2, twice the speed of sound, opinions are still divided about straight or highly swept wings, or the more favored delta. For the future, new ideas are on the drawing board. Vertical takeoff and landing to overcome some of the low-speed difficulties. Already, military aircraft exist, which will change shape during flight, from straight-winged at lower speeds to highly swept at supersonic speeds. Shapes like these may one day fly passengers at speeds much faster than sound.
If you think the financial...
Well, what did we think of that then?
Fantastic video.
Yeah, it kind of explain, even though it's ancient, it explains things pretty well. And that bit at the end, I'll let it run for that, because a lot of the designs, a lot of the shapes, you can actually see being used nowadays.
Exactly. Yeah.
So, you know, it's quite good, and it explains a lot of the problems of high-speed flight and how those shock waves are forming. Explains them quite well, I think. So what we're looking at now then is just highlighting, you know, what we've seen, some of the problems that we encounter and how we can overcome them. Yeah. It's said that when the shockwave forms and the shockwave travels back, and behind the shockwave, we get all that turbulent air. If we allow that to form on the aerofoil, the control surface that's behind in all that turbulent air is going to be quite ineffective. Yeah, and as the shockwave travels back as well, it can settle around the hinge area of the control surface. Again, you know, having that shockwave on the control surface hinge, it talks about the elevator in the notes. Elevator will do. That's going to reduce the effectiveness even more. So if you can imagine your shockwave there, you've got a lot of turbulent air behind that the control surface is trying to act in. That air is no use aerodynamically, so it's going to have no effect. And the shockwave sitting on the hinge point is going to make the control very difficult to operate. Yeah. So as it's said on the film there, one of the ways we can get around that, certainly for the elevators, is to use an all-flying tailplane, a slab tailplane, so that the whole tailplane moves rather than the control surface at the back. And that was one of the things.
Stabilizer.
Sorry?
Whole moving stabilizer.
That's the one, yeah. So the whole thing's going to move. Yeah. So if that's the back end of your aeroplane, the whole stabilizer is going to move rather than having a control surface trying to do it. Yeah. So we're going to move the whole thing. When they first tried to break the sound barrier, when they were going through it, that was one of the things that the UK actually discovered. And then because they were meant to be working with the Americans, they told the Americans about it, and the Americans just stole the idea and claimed claimed all the glory for it, which is one of the reasons one of the multiple reasons I dislike the Americans.
Multiple reason.
Yeah. They won't let me into America because I went to Sudan. So I'm a banned person from America. Woohoo! Yeah, so higher speeds, yeah. Remember that we'll use the all-moving tailplane to overcome the problems of pitch control. Yeah, full and accurate control. Some aircraft, as we said, will use differentially operated tailplanes, so we can double up the tailplane as an aileron as well. The aircraft I used to work on, the Tornado, was good for that. It was a high-speed aeroplane, had an all-moving tailplane, and it would move differentially as well. Didn't have ailerons on it; it just had spoilers and the all-moving tailplane. And that's a concept that's being looked at again in civilian world for high-speed flight. Yeah, so we can now go from, I don't know, New York to Australia in 3-4 hours. You know, or that's the sort of things that they're looking at. So that's your problem with your pitching control. Yeah. Tuck under. Boom. Where was I going with tuck under? With an aircraft, the center of lift is behind the center of gravity. Yeah. So the aircraft tends to fly nose down. Yeah, the aircraft has got a tendency to fly nose down under normal circumstances. So what happens is we put a downforce on the tailplane that pushes the tail down, brings the nose up, allows us to fly straight and level, and that's just part of normal flight. Once you get into the high speed region, yeah, if we allow the shockwave to form, the turbulent air coming off the wing is going to hit the tailplane. And what that does, it changes the effective angle of attack of the tailplane. So instead of putting a downforce on the tail, there becomes an upforce, and that causes the nose to tilt down even more. And that phenomenon is known as tuck under, sometimes called Mach tuck. Yeah. And as I say, that's caused by the downwash, nose down attitude of the aircraft as the air's coming off the, as the air's coming off the tailplane, the main plane, behind the shockwave, that turbulent air stops the downforce, the downwash. Yeah, we get the effective change in angle of attack, so that the pitching becomes even worse. Yeah, and that is known as Mach tuck or tuck under. So what we need to do is to shift the tailplane so it's not going to be affected by that phenomenon. Yeah, known as well, it's part of the longitudinal stability, but the way it happens is what they call the Mach tuck or the tuck under. Yeah, and there's a bit that we need to highlight. Yeah, so no downwash acting on the tailplane. Tailplane now produce an upload together with the nose down movement produced by the wing. Yeah, the nose pitches down even more. You tuck under. Tuck under, I've seen crop up somewhere. So stick your highlighter through tuck under and just understand how that's happening. Yeah. And as I say, on the question that I saw, I can't remember the exact wording of it, but it referred to it as Mach tuck. Yeah, it's exactly the same thing.
On which page, sir?
Page 82 at the top. Oh, I know what it was. Yeah, it's to do with the lateral the trimming. We'll come on to it in a minute. I've remembered it now. Yeah. What can we do to prevent tuck under? And that's we move the tailplane, but we can also get rid of it by trimming. Yeah, by Mac trimming. So when I remember the question fully, when I see the bit, I'll remind you. But understand what tuck under is. It's the effect on the longitudinal stability by the shockwave creating turbulent air, and that turbulent air striking the tailplane. Barrow. Yeah. Other effects we're going to get on stability. Yeah, the shockwave isn't necessarily going to form on both wings together at the same time. Yeah, so if we get the shockwave forming on different wings at different times, that is going to affect the handling of the aeroplane quite a lot. Yeah, it says on the slide that the airframe will fly one wing low, but again there'll be an awful lot of buffet and a possibility of stall on one wing. Directional stability, yeah, we've got that difference in drag on the opposite wings. Yeah, so again that's going to affect the directional stability of the aeroplane. Yeah, that as it says in the notes could lead to your Dutch roll jobbing in. There is another bit I need to mention. Yeah. Where are you? Where are you? Where are you? Yeah, up on page 80, it talks about aileron control reversal. Yeah. I've lost my picture of that. What happens with the control reversal? Yeah. If you imagine that's your wing with the aileron on the back of it. Yeah, everything's trogging along quite happily. If I put the aileron up into the airflow is striking that now, and it's trying to push that aileron back down. But as it's trying to push the aileron back down, yeah, it's twisting the wing, so that the nose of the wing is going to come down. So if you can imagine the airflow striking the aileron, it's going to cause the wing to twist nose down. As it twists, what happens is the angle of attack changes. So instead of producing more lift, it reduces lift, so the wing drops. So when the pilot's flying along and he moves the control column, expecting one wing to rise, yeah, because of the effects of high speed flight, yeah, and at the wing tip, yeah, the structure's a lot thinner at the wing tip. So as he tries to move his aileron, yeah, we get that twisting effect. So rather than the wing going up, the wing will come down. So one of the ways we get around that is to have two sets of ailerons. Yeah, we have the what they call the low speed aileron, which is the outboard aileron, which we lock into the neutral position above a certain speed, and then we have the all speed ailerons. Yeah, because they're in the thicker section of the wing, there is less tendency for the wing to warp and to twist. So that's how we get over the problem of control reversal. The outboard ailerons are locked in position. What else do I need to say? Not a lot else there. Yeah. Again, just the different designs. As you can see, as we get towards the wing tip, the wing becomes a lot thinner. So structurally, it's weaker. So by locking out the the outer ailerons, we avoid that twisting moment in the wing. The all-moving tailplane, yeah, we can still fit elevators at the back of the tailplane for low-speed control, but for high speed, the whole thing is going to move, the all-moving tailplane. And again, we'll vary the angle of incidence on that, as we mentioned yesterday, I think it was. Yeah, and then the thing a lot thicker at the wing root. And if we have that supercritical wing shape, again, that's gonna help us out enormously. Tuck under, yeah, we mentioned that. To correct for that nose tuck under that we're talking about, yeah, this is where I was trying to think of. To correct for tuck under at transonic flight, we need to change the pitch trim quite often. Yeah. So what they do in the aircraft is they provide a Mach trim system, and that automatically moves the tailplane to the correct point. Yeah. It says the illustration shows an example of Mach trimming on a supersonic transport aircraft. That's the other method that they use. So we've got the Mach trim, where we're going to move the tailplane, trim that. But another method is by shifting the fuel around in the aircraft, and that's keeping the center of the pressure and the center of gravity as close to each other as we can. So during acceleration from subsonic up to supersonic speed, yeah, the nose down trim change is corrected by transferring fuel from a forward tank to a rear tank. Moves the center of gravity rearwards, and that removes the nose down trim change caused by the move of the center of pressure. As we decelerate, as we come from supersonic down to subsonic speeds, again, what we'll do is transfer the fuel from a rear tank to a forward tank. Those tanks used to be dedicated trim tanks. Concorde was a good example of the trim tanks, but even today, a lot of the larger transport aircraft do use fuel management as part of the trim system. Yeah, again, we can use the all-moving tailplane for trim as well. Yeah, so don't forget, correct for nose tuck in transonic flight, frequent pitch trim changes are moved. Mach trim system using the all-flying tailplane will adjust the position of the tailplane to compensate for that. Yeah, and fuel management again is helping us to trim the aircraft as we snot along. Ding ding ding. Area rule, yeah, that was just your trim tanks. Yeah, we're just moving fuel from the main tanks back to a trim tank. Putting that fuel in the rear trim tank is keeping the tail of the aircraft heavy, which is keeping the nose up. Yeah, if we didn't have that, the tuck under would force the nose down. The area rule, as it mentioned on the film, area rule is there to reduce drag at high subsonic and during transonic speeds. And all we're doing is just making sure that there's a lovely smooth cross section to the aeroplane. And one of the ways to do that is to put this wasted area on in the fuselage to accommodate the root of the wings. Yeah, and it's purely there to reduce the drag on the aeroplane, changing the cross-sectional area. Yeah, make sure that the total cross-sectional area changes gradually to give us that nice smooth profile. Yeah, no large lumps and bumps sticking out. So if that one does come across, what is the purpose of area rule? It is to reduce drag. Yeah, and that's what they're trying to show us. Yeah, we want a nice smooth profile. I can't really explain it any better than it did on the film, but just making sure that we accommodate everything within a nice curve on a graph, rather than having bits and bobs sticking out. Yeah, by wasting the fuselage of the aircraft, we can now accommodate the wings, and that brings us all within the boundaries that we were talking about. Yeah. Increase the fuselage cross-sectional area. Yeah, waste it in wings. Again, we're increasing the potential for drag. Taken from an old slide, but you can see how we're cross-sectional area. Yeah, you've not got a very smooth profile. You've got these lumps on it, whereas by wasting the fuselage to accommodate the wing, yeah, we're giving it a much smoother profile, smoother area, keeping the cross-sectional area within a limit. Again, that's just there just because it highlights the wasting of the fuselage to accommodate the wing section. Ta-da. Yeah, our aircraft, obviously, as the aircraft gets faster and faster, the airflow going across the skin of the aircraft is going to generate heat, and the faster we go, the more heat that's going to be generated. So when we're designing our aircraft and we want to fly at a particular speed, we've got to make sure that we manufacture out of suitable materials. And at the moment, we're kind of limited because the materials that we're using, your aluminium alloys and what have you, yeah, they're suitable up to Mach 2, but anything faster than that, the surface temperature is, pardon me, just going to rise too high. Having said that, the development of materials, pardon me, that we're going to work with nowadays, it's coming on in leaps and bounds, which is why we are coming back toward more and more towards supersonic flight. Yeah, the materials that we can utilize, the design concepts now. High-speed flight is something that they are really going into with a passion. Yeah. Once Concorde went, everything sort of died down in the high-speed flight region, apart from the military concept. But now people want to get from A to B a lot quicker. So if you're going on your holidays, yeah, you want to get to your destination a lot faster. So high-speed flight is something that's starting to make a bit of a comeback. Yeah, once we go into supersonic flight, yeah, we're going to have a big change on the effects of the air that's flowing around the aeroplane. Yeah. Speed, as the speed of the aircraft increases, yeah, we've said and we've seen how the shockwave tends to move backwards, and the turbulence behind it's increasing. Yeah. Once we're at that point, as the shockwaves move to the rear of the aerofoil, the airflow around the aerofoil is all supersonic, and then forward of that, we're going to get another shockwave starting to appear. And that's what they call the bow wave. The original wave, the trailing edge, yeah, again starts to angle out. Speed's further increased. The bow wave that's formed will attach itself to the leading edge. Yeah. When the airflow meets the shockwave, it loses speed, changes direction. We said that there's a sudden increase in pressure, density, and temperature. A loss of energy, more thrust required to make up for that. That was what we called our wave drag. Yeah, so the airflow going across, shockwave forms, Yeah, airflow becomes supersonic. That shockwave starts to move towards the back of the aeroplane. We said that the effects of the air going through that shockwave were going to give us that increase in drag, that wave drag. Yeah, and now as we increase in speed, that shockwave travels towards the back of the aerofoil. Yeah, so the airflow over the whole thing in front of the shockwave is now supersonic. Yeah, that shockwave is going to travel to the tail of the aerofoil. Yeah, and it's going to what they call fishtail. Yeah, so the area of flow turbulence behind the shockwave is now behind the aerofoil. Yeah, so we haven't got that drag over the aerofoil now. Yeah, we now get a bow wave forming. Yeah, and eventually that bow wave is going to attach itself to the front of the aerofoil. Yeah, the more it attaches, the more it's going to angle back. Yeah, the tighter the angle of attachment becomes, the faster that the aircraft flies. And now the tail wave has actually gone behind the aerofoil. Yeah, so supersonic airflow, it talks about subsonic airflow and supersonic airflow going through a converging, diverging duct. All it's doing, it rabbits on about this, but all it's doing is just showing how the air is affected. Yeah. If we put a subsonic flow into a converging duct, yeah, that flow will accelerate. The pressure will decrease because, well, it's good old Bernoulli, isn't it? Yeah, kinetics increasing, so the pressure energy is going to decrease. Density of the air will decrease a bit as well. In the diverging duct, yeah, that airflow is going to slow down, and the pressure will rise. Density will increase again. If we go supersonic, if we push supersonic air into that duct, yeah, as it goes into the converging duct, the flow is going to slow down. You've got all those molecules racing to try to get through, and they're just blocking each other up. So that the flow slows down, and the pressure and the density will increase. Yeah, as it goes into the diverging part of the duct, yeah, the velocity will increase, and the pressure and the density will decrease. The way I explain it to the ab initio guys, yeah, you got your converging, diverging duct, yeah. We know for subsonic air, as that subsonic air comes in, that the speed is going to increase and the pressure is going to decrease. As we come out, yeah, the speed will decrease and the pressure will increase. With supersonic flow, the opposite happens. So if you think about a bunch of runners going into a tunnel, yeah, normal circumstances, yeah, let's say they're doing a marathon, as they go through the tunnel, yeah, they're going to run in. There's going to be lots of runners, but they're all going to go through nice and sweet. Yeah, they'll crowd up a bit, but they'll go faster, so that they're not causing a blockage. You'll get less runners going through. Yeah, and then as they come out the other end, all those little runners are going to slow down a bit. Yeah, and the rest of them can catch up. If you're doing it as supersonic flow, all those runners are trying to get through the tunnel at once. Yeah, so you're going to get a big build up, and they're going to block each other in. Yeah, so at supersonic speed, if they're sprinting through the tunnel, they're all going to get there at the same time. They're all going to squeeze up. Yeah, that in turn is going to build up the pressure. Yeah, the more runners, the more pressure, the more squeezed in together they are, and they can't run as fast. As they come out the other end, the opposite's going to happen. Yeah. So the supersonic flow is having the opposite effect to our subsonic flow after all that waffle. Yeah, we've just seen that, talked about that. So your converging duct, you're going to increase velocity, decrease pressure, density will remain the same. Converging duct, the velocity is going to decrease, the pressure and the density are going to increase. Diverging duct, the opposite. Yeah. So, ba-dink. Yeah, that shows you what we're just talking about, summarized in a little chart. As the flow around the aerofoil increases, yeah, the angles of the shock waves become more acute, and we just saw that on the picture. The various types of shock wave occur in supersonic flow. Yeah, so we're whizzing along. Yeah, the faster we whiz, the more the angle of the shock wave, that angle becomes more acute. There are different types of shock wave that can occur in supersonic flow, and the type of wave that's formed depends upon the flow and the shape of the object that flow is trying to get around. So on the bottom of page 87, stick your highlighter through the bottom bit there, please, the bullet points. 3 types of shock wave, or 3 types of wave, I should say, in supersonic flow. We have the oblique shock wave, yeah. We have the normal shock wave, and we have an expansion wave. And they are the 3 types of wave, and it just depends on, as it says, how the airflow is meeting whatever. Your oblique shock wave, yeah, we're flowing into a corner, yeah, and as we flow into the corner, the direction of the airflow is altered, but the speed and the what have you remains the same. Yeah. Let's see if we can explain that a bit. Yeah, the supersonic airflow is turned into a corner. The shock wave forms at the corner. The airflow slows down, but the speed of the airflow behind the shock wave is reduced, but the flow is still supersonic. Yeah, the airflow changes direction, but it follows the surface, and the pressure, the density, and the temperature of the flow behind the shock wave increases slightly. Yeah, your oblique shock wave. So we're going into the corner. Normal shock waves normally form at 90 degrees, but as we travel and we start to meet our aerofoil, yeah, that wave is going to start to bend. It says then if we put a blunt nose body in front of a supersonic airflow, the shock wave will form in front of the leading edge. Shock wave forms perpendicular. It's known as the normal shock wave. Airflow behind that shock wave subsonic. It's been slowed down. After passing the blunt nose, it may remain subsonic, or it may accelerate to supersonic speed. Yeah. The speed of the airflow behind the shock wave depends on the shape of the nose and the Mach number of the free airflow around it. Yeah. So the following changes take place when supersonic airflow passes through a normal shock. The airflow is slowed down to subsonic. Direction immediately behind the wave is unchanged, and the pressure density and the temperature of the airflow increases. Yeah, so that's our shock wave building up. The normal shock wave, yeah, the air behind it, subsonic, yeah, and that shock will then start to turn oblique as it approaches the front of the object, I should say. Yeah, the sharper the object that we're going to meet, that is going to have an effect on the shape of the oblique shockwave. And as the oblique shockwave travels in, the airflow that's being diverted around, the effect of that change of direction is going to be a lot less marked. With the expansion wave, the expansion wave isn't a shock wave, but what's happening again as the flow goes around a corner, it's changing direction, but it's not having any major effect. So the flow around the corner doesn't cause any sharp changes in the airflow, so a shock wave doesn't form. The speed of the airflow behind the wave is greater. The flowing direction is changed. It flows along the surface, provided separation doesn't occur, which is fair dues. And the pressure and the density of the airflow behind the wave is decreased slightly. So your three types of wave, the oblique as we go into a corner, the normal shock wave at 90 degrees to whatever, and the expansion wave as we go around a corner. Again, the airflow will just follow the path. So long as we don't get to the point of separation, it'll follow nice and smoothly. So you can see with the changes behind a shock wave at supersonic flight, the air behind that shock wave is all supersonic, so there's not going to be any great effect on the aerofoil. It then goes on to look at the different, gives us a couple of different patterns that we can look at, and it just explains what's happening. So if I had a big flat plate and I put that at a slight angle, at the front of the thing, I'm going to get an expansion wave and an oblique shock. The rear, I'm going to get the same button flipped over. So then we go A, B, C, D. It's just showing you the lift that's being generated at high speed over those particular objects. That double wedge shape that we saw before, because it's got a nice sharp leading edge, we'll get the oblique shock forming at the front. The air travels over, we get the expansion wave, a nice smooth transit of the air, and the oblique shock at the tail. Shows you the pressure distribution, fairly even Stevens all the way over the thing. But if we stick that double wedge at a slight angle, give it an angle of attack, then the lift pattern changes dramatically. So we get a good lift distribution over the double wedge. The one that talked about the circular arc, where we've got a nice thin wing, but we've got a rounded front, we've got a rounded, smooth profile. Where we start off with an oblique shockwave at the leading edge. Then as the air travels over, it's creating an expansion wave, which again, because it's an expansion wave, we're not getting any detrimental effects. The airflow over the full thing is nice and smooth. And again, we're going to get really good lift distribution over that. Shows you the conventional blunt nose aerofoil, and behind the oblique shock wave, we're going to get a region of subsonic airflow, and again expansion waves back to the shock wave at the trailing edge. So all that little lot is just going through and showing us how supersonic airflow over the aerofoil sections affects it. The lift and the drag patterns. Remember the pressure distribution on the surfaces, the faster we're going, that increased pressure in the forward half of the curve, we're going to get that wave drag forming. So to avoid that, we want to have a design shape that's going to reduce that wave drag to as much as possible. There is nothing in there I can see that for exam purposes we need to worry about. Yeah, you need to know the 3 types of wave that form in supersonic flight. Yeah, you need to know your normal, your oblique, and your expansion wave. Yeah, the oblique going into the corner, the expansion around the corner, and the normal shock wave is what forms at the front. And then as we go faster, the angle changes; it becomes an oblique shock wave. Behind the shock waves, yeah, what's happening there with the air? Ding, ding. Nothing really else we need to say in there. Yeah, again, just taken from the notes, just showing the various lift patterns that are building up. Your obliques, yeah, your expansion wave going around the corner there. No net lift, but on that we've got that wave drag. Yeah, so the heat that's building up. Having to expend more energy to overcome that. That was your double wedge, yeah, double wedge pressure distribution, 0 lift, yeah, all even Stevens. Give it a slight angle of attack, yeah. Now the airflow flowing across, we're going to get good lift, yeah. Expansion wave, again, we're going to get the lift at the rear of the airfoil, and then the circular arc type, yeah. Faster we go, the normal shock's going to form. Faster we go, we're going to start with an oblique shock, and then behind that it's all going to be expansion wave, and then just showing you the conventional aerofoil, a lot thicker. Behind the oblique shock, we're going to have a region of subsonic flow. Right. We saw how sweepback earlier was used to raise the critical Mach number of the aeroplane.
Sir, can we?
Yeah, and that sweepback, that delta. Sorry.
Can you have a break 10 minutes?
Can you have 10 minutes? Yes.
Yes.
So I'm at that 10:40, 11:40. I'll say sorry. So 11:50, 10 minutes. Yes, by all means.
Okay, sir. Thank you, sir.
Okay, no worries. 10 minutes.
Mr. Jim, you there?
I'm here, yeah.
How can be Mac talk removed?
What did we say we're going to use to get rid of Mach talk?
I didn't got it
trim.
clear, so I'm asking you.
We're going to use Mach trim. Yeah,
Okay.
so that we're going to trim the horizontal stabilizer, the all-flying tailplane. Yeah, so as we go up through the transonic range to the upper reaches of transonic, yeah, that tendency for tuck under, we'll get rid of that using trimming of the tailplane, yeah, and we can use movement of fuel as well. Yeah. Okay. Just let me. Yeah. So page 82.
82, yeah.
Yeah. Yeah. So by moving the whole tailplane, yeah, any disruption of the airflow, that moving of the tailplane will give us the correct trim, and also by moving fuel from front tanks to rear tanks will do it as well. Yeah, so yeah, part of your Mac trim, yeah, keeping the aircraft trimmed, doing away or negating that tuck under. By careful fuel management, what we're going to do is move fuel from a front tank to a rear tank. Putting the fuel in the rear tank is going to keep the nose of the aeroplane up. Yeah, as we slow down, yeah, we can move that fuel back.
All right.
Okay with that?
Okay.
Yeah, that was how it did it with Concorde.
Mm-hmm.
This series, the transonic range was described, in which the airflow around the aircraft is mixed, part subsonic, part supersonic. The dark green represents regions of subsonic flow, the light green supersonic. Shock waves are shown in red. This film is about the much more straightforward supersonic range, where the main flow everywhere is supersonic, shown as before in light green. To understand supersonic flight, it's necessary to examine the nature of supersonic airflow, which behaves more simply than subsonic. First, consider what happens when a single point is moving supersonically. Pressure waves sent out continuously at the speed of sound form a round cone, the Mach cone. The lines forming it are called Mach lines. The half angle of the cone is called the Mach angle, usually shown by the Greek letter mu. The size of this angle depends on the ratio of the point's forward speed to the speed of sound. That is, on the Mach number.
And as long as you can throw it in a straight arm motion and you have the right grip, it'll spiral.
Different things click with different people.
At Mach 1, the Mach angle is 90 degrees.
And to be able to find what clicks with you, it's a gift.
As the Mach number is increased, so the Mach angle grows smaller.
Playing video games is fantastic. I never understood it, His
A
mother
similar
never
effect
understood it.
can be
We
seen by
hated it
dipping the
for
point of a
years.
pencil in a
And
fast-moving
we had
stream of
absolutely no
water.
expectation that
Only
he
the
would
region
actually be
inside the
good at
wave
it.
is influenced by the pencil point. The water outside this region flows on as though no disturbance existed.
Team knows each other. So when
In the same way, the supersonic point can only affect the air lying inside the mark lines, shown here in white. Ahead of the mark lines, the air is undisturbed. Since all the disturbances coming from the point are infinitely small, the speed and direction of the airflow, shown here by white streamlines, don't change as the air passes through the mark lines.
We could have got into, and I couldn't be happier.
But what if the disturbance is large? Such a disturbance is produced by a leading edge in supersonic flow. An oblique shock, the bow wave, is formed. How does the flow behave as it passes through such a shock wave?
To the pros, PUBG Mobile is because
Consider
they want to
first the
become
diagram
the best.
of a
They want
normal
to be
shock
that
wave.
#1 player in the world.
This, at right angles to the flow, always slows it down from supersonic.
The best thing about
subsonic.
this big organization is
Speed is
scene.
represented by the length
It's
of the arrow.
abilities that they're able to give, the opportunities they're able to give to the players.
Here's an analogy.
Players are able to focus
This
more in the
toy
game,
animal
practice
walks down
more,
a
and
sloping
work together
board.
as a team, and
Faster
ultimately
down the
push
steeper
to be
part.
the #1 team in the world.
And then slower.
There's always a lot of pressure to kind of represent your organization. I think it's honestly kind
Here's
of a
the
good
same
pressure
thing seen
where,
from directly
if
above.
you don't have that push in
Supersonic,
you, then you might not be as
subsonic.
motivated, or you'll get complacent with how you're performing. And with being in Cloud9, was
If
kind
the
of
whole board is now
pushed us to
pushed
make sure that we're always
sideways,
getting better as a
the
team
animal's
and,
path
doing the
across
best that
the
we can.
screen is a straight line which bends suddenly.
Should this tactical zoom lens be made illegal? This is the first reason.
Just the same way, imagine a uniform sideways velocity superimposed on the airflow. This will not be affected by the shock wave and will be the same on both sides of it. The resultant airflow is now like this, exactly as it was for the animal. It's now supersonic past the shock wave, but slower than ahead of it.
It's only in esports
If
that
now
you're
the
able
whole
to play
picture
with,
is turned
players on your
round,
team that are from
so
a different country
nothing
or
is changed.
continent in our case.
The shock wave is
I mean,
oblique
it's
to the
just really
airflow
cool, and it's not something you can see.
and has deflected it and slowed it down. Pressure always increases when velocity is lower.
For a long time now, but we've really got to meet in tournaments in Malaysia.
And if streamlines are drawn, they are closer together past the shock wave than ahead of it.
We kind of started talking, got to know each other, and like really
The shock wave can be caused by a solid surface with a sharp corner. The streamlines are parallel to the surface.
Hello, Jim.
Hello.
With the leading edge of a wing.
Are you playing a video?
Yes, I was.
But we cannot see the video.
I know, because you were having a break.
Oh.
So I was just looking to see if it would explain the supersonic as good as the other one, and it does. So
let's get a
I'll maybe stick it on. So it's
now.
only 15 minutes.
Yeah. Adder's not only good mechanically, but he's also got all.
I'll maybe use that to take us up to
pro player and
up to lunch.
Package, and we couldn't have picked up a better player.
I have a car in my spot, guys. So
hello, Jim. If these videos are in YouTube, please provide us link.
I head back north, meet up with you guys,
Okay.
and go over.
Okay, yeah, can do that instead.
So that we can watch these videos in some free time.
Это человек, который понимает, насколько важны взаимоотношения в команде. Он понимает, как важно всегда поддерживать свою команду и никогда не говорить ничего плохого.
Alright, Alright, I've got a nade, don't push yet. I'm gonna nade him. Alright, throwing it. Okay, you ready? Alright, let's go.
Конечно, помимо Беовульф в моей команде еще есть два прекрасных человека. Это Аныван и Пайра. Пайра — это просто кремень. Человек, который может молча выполнить все, что от него нужно, сказав за игру одно слово, и это будет слово «yes», когда мы ее выиграли.
Uneven, do you need pick up? Uneven. Smoke yourself, man.
А Uneven — это, наверное, самый близкий человек для меня в команде, потому что он так же, как и я, жил в Европе. Вернее, он родился там, родом из Франции, 7 лет прожил там и только потом переехал в Америку. Поэтому чувствуется с ним какая-то такая культурная связь.
Chasing. On the bridge right now.
It was definitely kind of outside the box, picking up a player from Russia.
Twin the car at least. They're shooting me. I'm good.
Instead of somebody from North America, like we were expected to do. It's something that's never been done before in PUBG Mobile.
Can we make it? Or should we just try to find a good fight, just to pick up some points?
Alright, circle's about to change, pay attention.
Многие люди в России довольно патриотичны, и поэтому, когда я ушел в американскую команду, мне зачастую присылали сообщения в духе «Зачем ты предал родину?» Как бы это... Ну, это моя карьера. Я пошел в другой регион, получать опыт, развиваться и...
Всех ребят я знаю достаточно давно. Еще в 2018 году я был буквально у истоков зарождения именно в СНГ PUBG Mobile как киберспортивной дисциплины. И это было самое, наверное, запоминающее.
Everybody happy, everybody.
Я наблюдал, как ребята, которые сейчас находятся на профессиональной сцене, буквально теряли веру, и казалось, некоторые из них навсегда уйдут, и даже представить не могли, какие перспективы ждут сегодня. Безумно приятно, что кому-то из них я помог.
That film that I showed you earlier, there's a follow-on part that is really good at explaining what goes on in supersonic flight. Explains it better than me, and it's got all the visuals as well. So I've sent Yadav the link to YouTube. So in your own time, if you wouldn't mind just having a look at that, just so you can get your heads around it. Yeah. And Mr. Yadav, because he's a wonderful, wonderful person, we'll send that link on to you guys.
Yeah, I have put it in group already.
You're a magic person. Thank you very much indeed.
Thank you, sir.
Right, so just to wrap this little lot off then, we've said that supersonically the air is going to behave differently. Yeah, and the three waves that it forms, the air is going to be a lot smoother. We're not going to get that turbulence or anything. And once we're into supersonic flight, we've gone above Mach 1. Yeah, there was that little diagram that showed us how the different aerofoil sections are going to behave in supersonic flight. If we think about our aeroplane, we talked about the aircraft earlier. As it's flying along, how good are my aeroplanes? Yeah, it's sending out those little pressure waves. And what's happening as we go supersonic, the pressure waves are forming behind the aeroplane, which is what the sketch is trying to show you. And they're growing and growing as the aircraft is traveling faster and faster. That series of pressure waves, as they grow up behind, is forming what they call the Mach cone. So the Mach cone is that sort of shape, and the Mach angle, is half the Mach cone. Yeah, so it talks about the Mach angle. We're talking about half the Mach cone. Yeah, the Mach cone is quite important because the airflow outside the Mach cone isn't going to be affected at all by the passage of the aircraft through, and the area within the Mach cone, the airflow has already been affected. Yeah, so if we can keep the profile of the aircraft within the Mach cone, everything that's flowing over that is going to be supersonic, and the supersonic airflow isn't going to have a damaging effect, if you like. So on page 93 of the notes, it's just showing, same as on the slide, showing that the point moving faster than the speed of sound, the pressure waves behind the aircraft. Yeah, so the point moving faster than the speed of sound, going from A to D. Pressure waves sent out when the points at A will travel out in all directions, but the point's moving faster than the speed of sound, so by the time it's reached D, all the pressure waves are behind it. Yeah, the tangent, it says, from D to E is going to be the Mach angle. Yeah. The greater the Mach number, yeah, the more acute that Mach angle is going to be. Yeah. Small pressure disturbances are left behind, and the shock waves again aren't going to have that detrimental effect. So what we want to do is to try and keep the profile of the aeroplane within the Mach cone. So anything that's traveling over the aircraft is already traveling supersonic, not going to affect us, and anything outside the Mach cone isn't going to have any effect, because the aircraft isn't going to be disturbing that air, because all the disturbed air is behind it within the Mach cone. Yeah, so different methods of keeping us within that region, though. We can use arrowheads, yeah, arrowhead deltas, a type of wing form, or what they call the Yogi delta, or OG delta. Yeah, you can see the shape of the Concorde wings on the slides there. That is the OG shape. Yeah, so the delta wing, large chord, low thickness to chord ratio, so that we've got very low wave drag. Yeah, and a delta wing is very strong and stiff. So structurally, it's more able to cope with the stresses that are going to be generated. The Yogi delta, the big advantage of the Yogi delta is it increases the stalling angle phenomenally. The stalling angle is huge, and during normal flight parameters, very unlikely to be achieved. So very difficult to stall the aircraft. It says the reason there, we're back to aerodynamics. Remember, we talked about vortices along the leading edge on a delta wing. Yeah, and those vortices increases, the angle of attack increases. So the pressure difference between the upper and the lower wing increases. So because you've got that pressure difference, the lift is changed. Beautiful example of the Yogi delta, or the OG delta. Yeah. Elevons at the back of the wing there that we talked about the other day. So all your controls via your elevons. Yeah, huge wingspan. But the pressure differential across there, yeah, giving you all that lift. Your chord length as well. Yeah, just going back on the notes there, it talks about the all flying, all moving tailplane. The effectiveness at transonic speeds, we talked about that. Seems to be out of nowhere. So page talking about the effect of tuck under tailplane. What we're saying, with the conventional one, the shockwave moves back. It makes the elevators ineffective. To overcome the problems of an ineffective, referred to as the stabilizer. Yeah, acts exactly the same, but that elevator low speeds. High speeds, the whole thing's moving. Yeah, I don't know why that's appeared there. I can only work for it in this country, the supersonic region, or maybe that's why it's been put there. Once we're in the supersonic region, an elevator would be totally ineffective. So we're going to move the whole tailplane to give us our longitudinal control. Yeah. No, I'll just say there. Has anybody got any questions on the all moving tailplane? I could have the supersonic thing, but personally, I'd have put that section a bit earlier. But anyhow, it's there. We've got the information. Anybody got any questions on that? Right, you guys have done module 15, yeah?
Yes.
Yeah, so when you did module 15, do you talk about high-speed intakes?
We have.
You have. So the last little bit then for us is just as part of the high-speed flight, we've got to consider what the engines are wanting and what the engines are doing. Yeah, so the shaping of the intake, the faster we go, needs to be taken into consideration. Performance of the engine, depends on the efficiency of the air intake, especially at high speeds. Gas turbine engines need lots of air to operate efficiently. So the intake's got to be designed to provide air to the engine, minimum pressure loss due to friction, due to that air becoming turbulent, and losses caused by the boundary layer separating from the walls of the intake, as shown here. We've got the engine, flying along straight and level. We've got nice uniform entry from the intakes into the engine. If we maneuver the aircraft, we're going to lose some of that intake of air because of the separation of the boundary layer. The engine's still going to get fed from the other side, but air intake's going to be, or the presentation of the engine is going to be affected, going to be reduced. So intake design for your high-speed aircraft is carefully considered. As you're aware then, if you've done 15, the air coming into the engine has got to reach the compressor of the engine at a uniform pressure across the whole inlet area. So to achieve that, we've got to slow the air down. The best type of intake for your normal turbojet at transonic or low supersonic speeds is the pitot intake. The pitot intake, the nice rounded one. Allowing the air to slow down, presented to the engine nice and uniformly, nice pressure, and again with these we can utilize aux air intakes to complement the air coming in. So by careful design, yeah, we can increase the compressor pressurized by compressing the air in the intake. That's known as the ram effect. Pressure increases as the forward speed increases. Increasing intake pressure increases the mass of air entering the engine, and that increases the thrust of the engine, so the performance is increasing. Yeah. Mach 1, the compression of the air caused by the ram effect, equal to that produced by the engine. Higher Mach numbers, the compression of the air in the intake is bigger, but the compression of the air in the engine decreases. Yeah, so ideal air entering the compressor should be subsonic with an even pressure distribution. We've said that. So the intakes are designed to decelerate the airflow to the correct level for the engine. Yeah, high speeds. What we're going to do in normal operating circumstances, we're doozy, but at high speeds, what happens is shock waves form at the intake of entrance to the intake. By careful design, we can control those shock waves and use those shock waves to slow down the airflow as it's coming into the engine. Yeah, that was one example. Yeah, what we're doing is the high speed air comes in. Yeah, we're actually creating little shock waves by shaping a bullet in the intake. As the air passes through those shock waves, it's slowing down. As it slows down, it's being presented to the engine at a subsonic speed, and at that uniform mass. Yeah, so we're kind of controlling the airflow as it presents. It does say for the ideal intake for your slow, low supersonic and subsonic speeds is the pitot intake. Yeah, the short round intake. Yeah, is ideal for what we need under normal circumstances. Yeah. Anything else I need to say there? Yeah. Downstream of the normal shockwave, the airflow is always subsonic. Flight speeds within the transonic range, the pitot type is suitable. The oblique shockwave doesn't slow down a supersonic airflow as much as a normal shockwave would. So at supersonic speeds, the airflow in the intake is slowed down by a series of mini shockwaves. Speeds above 1.4 Mach, the intakes are specially designed to produce these shockwaves, which is going to give the smoothest deceleration of the air. What we don't want is turbulence as the air goes through the shockwave. It needs to be presented nice and smoothly to the engine. So again, the designers look your normal intake. Yeah, for flying through the transonic speeds, low supersonic speeds, the air being presented to the intake. Again, the shaping of the nose of the intake. We said before we're going to allow the air to slow down. It's going to become subsonic. It's meeting at a nice uniform mass as it meets the front of the engine. Yeah. So again, the shaping of the intake is allowing for that. At higher speeds, yeah, we need to control the air. We need to build up these shock waves to slow the air down, but to keep that deceleration of the air nice and smooth. So by careful design and using little ramps that will alter the throat area of the intake, where we can build up a set of shock waves. So the faster we go, yeah, we can now, it says supersonic cruise. Yeah, the airflow is presented to these mild shock waves. It's slowed down, and the correct mass is also presented to the engine. by using the ramps, building the shockwaves, and again we can duct off any excess air so we can bypass the engine. And that's where we're talking about the diverging, converging ducts. Yeah, subsonic speeds, diverging duct slows down the airflow, increases the pressure. Supersonic speeds, a converging duct is required to slow the airflow and increase the pressure. The pitot intake, suitable for speeds up to 1.4 Mach. Yeah, it's doing as we want it to do. At higher speeds, because of that speed of the air, we're going to redesign the intake to what's the word I'm looking for? To not adjust, to alter the pattern of the air to suit what we need. Reform it. I can't think of the word I'm looking for now. Yeah, but with your supersonic engine, yeah, the intake, the internal external compression intake produces a series of mild shockwaves that don't reduce the efficiency of the intake too much. Supersonic cruise, compression ratio of the intake much greater than the engine compressor. Designed for maximum efficiency at high Mach numbers, wouldn't allow enough air to enter the engine. So at high Mach numbers, the intake has that variable throat that we've just talked about. And as well as creating those shockwaves, it is changing the volume of air that's being presented to the engine. The intake's rectangular at the front and circular where the duct meets the engine, so it's changing profile during its length. The ramps vary the throat area, vary the spill out. Takeoff and subsonic flight, the ramps are flat so that the throat area is equal to that of the engine. Any additional air coming in through auxiliary doors, speed increases, the ramps lower, reduce the throat area, and at predetermined Mach number, the ramps allow the shock to move into the intake. We used to have big problems with the ramps, so that the speed of the aircraft was limited depending on what was going on with the ramps. Yeah. Shockwaves need to be kept at the throat of the intake, done by again opening that bleed duct that we're talking about. Yeah, we're creating the shockwaves, we're creating the mild shockwaves, we're bleeding off the excess air, we're reducing the throat area of the intake. So now we've slowed that air down through the shockwaves, and it's being presented at the right volume to the engine. Yeah. Take off your ramps are going to be flat. They're going to allow the maximum amount of air through. Auxiliary doors, again, should we need any additional engine. And then when we shut down, spilling off any excess air, so it's not going to have any effect. Engine has to be shut down in supersonic flight. The air spilled overboard through the spill door on the floor of the intake, and the ramps are lowered to the maximum down position. So if we need an engine shut down during flight, yeah, again, we're just protecting the engine. We're getting rid of all that, because even though the engine's shut down, yeah, the air's still going to be flowing into the intake. So what we're going to do is deflect as much of that air as we possibly can, so it's not flowing through the engine, it's not going to damage the engine. And again, through there, problems of intake design. Yeah, the intakes have sharp edges, yeah, low speeds, again, exactly the same as we had with the wings. The sharp edges can present problems. High angles of attack at low speeds, the airflow may cause the intake may cause a stall, causing the engine to surge. Yeah, so again, there's not a lot I can say about that. It's all down to the designers. Yeah. Not a lot else I need to say about that little lot, but just typical intake design. Yeah, the sharp edges. You can see the ramps in there that are going to be used for varying the throat area at the speeds. The engines are circular, so the duct shape will change as as we get towards the front of the engine. Sharp edges, yeah. So at low speeds, you've got to be careful that the engine doesn't surge. So we've got to keep as much air going in there as possible at low speeds. I can't genuinely think of anything else to say there. This is a nice example, even though it is military. Yeah, all the nice rounded surfaces. So we're raising the M crit. We can sweep the wings back to keep us within the Mach cone. So now any airflow going over the aircraft is all supersonic. It's not going to have any effect on the handling of the aircraft. All the disrupted airflow is behind the aeroplane. And so long as we stay within the Mach cone, the air out with that Mach cone is going to be totally undisturbed by the passage of the aircraft through it. The tailplane, the all-moving or the slab tailplane, used as a control. The whole tailplane is going to move, and that tailplane is out of the same area. So the air passing over the wing, yeah, at low speeds as we go through the transonic, that air passing over the wing isn't going to be as disruptive on the tail as it would be if it was in line. And that pretty much, guys, was high-speed flight. I can't think of anything else to say. Probably the best thing to do, just to make sure that I've explained it to your satisfaction, is to have a watch of that wee film when you get 10 minutes. Then if you've got any questions, come back and I'll try my best to answer them. But at that point, has anybody got any questions at all?
Yes, Jim.
Yeah.
Can we go to the page 93 and 94? What are the highlighted part? Because that time we were having some internet issue.
Page 93.
Yes, and 94.
Yeah, the Mach cone.
Mm-hmm.
Yeah. What we're saying about the Mach cone. Yeah, the greater the Mach number, the more acute the Mach angle becomes. Yeah. The shock waves. In fact, there's not a lot to highlight on 93, 94. Yeah. Sweep back, we said, raises the critical Mach number of the aeroplane. Yeah. Mm-hmm. So sweep back will keep the wings within the Mach cone, and a big part of sweep back. Once you get to a certain point, we can change that sweep back into a delta shape. So anything that's inside the Mach cone, the air flowing over it is all supersonic. Everything, all the turbulent air is behind the aeroplane, so the flow over the aircraft is a lot smoother. There's no disruption there. The Mach angle is half the Mach cone. Yeah. Yeah, not a lot else there. The delta wing. We just talked about the delta wing. Basically, we've swept back, and we've eventually come to the delta shape. The two types of delta, there's the arrowhead delta or the OG delta or the OG delta. Yeah, the OG, the big advantage of the OG delta is stalling is very unlikely on the aircraft because of the vortices it produces. and that was about it. And then the other bit was page 95. That was the all-moving tailplane. Because an elevator is going to be aerodynamically ineffective at high-speed flight. Yeah, instead of having an elevator, moving the elevator, we just move the whole tailplane. The whole tailplane then becomes the control surface. Yeah, we can have an elevator stuck to it, but that elevator will be used for low speeds. Yeah, tailplane, the all-moving tailplane, often called a stabilizer. Yeah, elevator not under the control of the pilot, but positioned according to the movement of the stabilizer. We'll have a look at that on Monday. Yeah, so the high speed, the all-moving tailplane or the stabilizer gives you much more efficient pitching control. Is that okay? Has that answered your question?
All okay.
Yeah, all okay with that? Right, I make that 12:20, so we'll have an hour for lunch. 13:20 for me. I'm not sure what time for you. About 1900, roughly the same time. There or thereabouts. What we'll do this afternoon, we'll have a look at the start of book 2. Yeah, a lot of it is kind of repeated from what we did the other day, so it won't be anything too dramatic. It'll be a nice steady plod this afternoon. Okay with that? Yes, Jim? No, Jim?
Yes, Jim.
Right. I will see you in an hour then for we'll have lunch.
Okay, Jim.
Right, howdy hi. Hope we've all had a nice lunch. Hope we're all fighting fit. All right, for this afternoon's little adventure together. Wonderful, wonderful, wonderful. Right, what we're going to do this afternoon, we've looked at the theory of flight. Yeah, and while it's on my mind, has anybody got any questions on the theory of flight side of things?
Hello, Jim.
Hello.
Hello. Hello. In this wave, the types of wave, I have completely understood this oblique shock wave, abnormal shock wave, but I am not getting this expansion shock wave. Expansion wave.
The expansion wave is just as the air is flowing around an outside corner.
Okay.
Let's have a look. Yeah. Let's I don't know. That's the edge of a I don't know, a wing or something like that. Yeah. With the expansion wave at supersonic speed.
Yes.
Because the air is traveling supersonically, yeah, if it goes into a corner, it's going to follow that corner around. And it's exactly the same with the airflow going around an outside corner. The air is, it hugs the corner that it's going through. But as it's going round, the streamlines are separating a little bit. Yeah, so they're getting a bit wider apart, which is where that expansion bit comes in. Yeah, the expansion isn't a shock wave, but it's just the smooth passage of air around an outside corner. If we're going into, let's say, an inside corner, yeah, the airflow is going to follow it round. Follow the corner round. But as it's doing so, it's setting up a what they call the oblique shock wave. Yeah, so at the start of an aerofoil, for example, yeah, as the oblique shock wave forms, yeah, the air behind that shock wave is still supersonic. So now that air is going to just follow it'll come through the shock wave, but it'll follow the contour of the shape without all the distress that slower air would go through. So as it goes through the shock wave, it slows down, but it's not having that disrupted effect. Yeah, that video link that was sent out that explains it quite nicely. Have a watch of that, and again, if it's if you're not happy, come back to me. But it explains it quite well. But all that's happening with the expansion wave is the air's flowing around a corner, yeah. But the streamlines are just separating slightly as it goes round, but they're still following the contour of the disruption.
Okay, Jim. Thank you.
Sure. Okay. Anybody else before we kick on? Right. This afternoon, then we've looked at the theory of things, and now we're just going to have a look and see how we can put that little lot into practice. Yeah. So we might find that there's a bit of repeated information, but we kind of need to go through it. And again, if there's anything I'm particularly familiar with, I will give you a shout and let you know. So the flying controls on our aircraft then. Yeah. As you're all aware, yeah, we need to provide flight controls. And those flight controls are going to maneuver the aircraft about the 3 different axes. This one, it mainly will come up in some form or other about what the ailerons do, about what axis does the elevator operate, something along those lines. So make sure that you know your axes and you know how the aircraft, rotates around them. So the ailerons, yeah, you're getting lateral control, but that lateral control is happening about the longitudinal axis. That is your rolling movement. Your elevators are giving pitching control. They're providing longitudinal control about the lateral axis. And the rudder is giving us directional control about the normal axis, or yaw control, or directional control about the yaw axis. The normal axis, the yaw axis, the same thing. Yawing movement around the directional axis. Spoilers on top of the aeroplane. We looked at spoilers, and the spoilers are there to assist the ailerons, giving us roll control. Yeah, and we know that the spoilers are the flat panels sit on top of the wing, hinged at the forward edge. They'll rise up, reduce the lift over the wing, increase the drag. Flight spoilers and roll spoilers, speed brakes and roll spoilers. Yeah, flight spoilers operated differentially by the aileron system. Yeah, if we're going to use them in the speed brakes, they will all raise simultaneously. Control surfaces depends on the aircraft type. Some are arranged in pairs, giving us duplication. Some single control surfaces, but multiple means of operating them. So our main axes, roll axis, lateral control, pitching, longitudinal control about the lateral axis, and directional control about the yaw axis. Yeah. Again, the various layouts of the control surfaces. Yeah, so the control surfaces on the rear of the wing, the leading edge devices. We've got the elevators, and the bit you can't see up above that, the rudder. Yeah. Again, just an example of the layout. Yeah, roll spoilers. We've got the ailerons there. Yeah, spoilers will be helping the aircraft roll. We've got the elevator at the back of the trimmable horizontal stabilizer. Yeah, and the rudder giving us our directional control. Just make sure I haven't missed anything there. Happy with those. Elevons, yeah, we looked at elevons yesterday, and we said that on delta wing aircraft, the control surface on the trailing edge acts as an aileron and an elevator, and that combined control surface known as an elevon. Control column move backwards or forwards. Both the surfaces move together as elevators. Control wheel turn clockwise or anti-clockwise. One elevon's raised, the other's lowered, and they will act as ailerons on our aircraft. They are interconnected so that pitching and rolling can be produced at the same time. So as we said yesterday, if the aircraft's taking off, yeah, it's got both elevons in the up position, which is pushing the tail down, which is causing the aircraft to climb. If I wanted to roll the aircraft at the same time, what I would do is lower the elevons on one side to create more lift on the other, which would still allow me to pitch the aircraft, but it would allow me to roll the aircraft at the same time. The flaperons, we talked about those, and the flaperons sometimes use inboard ailerons, and those inboard ailerons will droop. They will act as flaps. Yeah, so the flaps are lowered for takeoff and landing. The flaperons will droop as well. The primacy for them, though, is their function as ailerons. So when lowered, the flaperons retain their function as an aileron. And outboard ailerons are often designed to droop as well when the flaps are lowered. Yeah, just giving us that additional lift for lower speeds. Your flaperons. High lift devices. Yeah, again, we looked at high lift devices. Reducing takeoff and landing distances. Yeah, your large jet aircraft equipped with high lift devices. Double or triple slotted extension flaps on the much larger aircraft attached to the trailing edge of the wing, combined with either leading edge slats, Kruger flaps, or sometimes leading edge flaps. Variable camber leading edge flaps, depends on the aircraft type. But your larger aircraft will have some form of leading edge device and trailing edge device. Slats, we said, I've got the extra position, so slats for takeoff. The slats and the leading edge flaps are extended. For landing, the slats extend further to further improve the camber of the wing. Yeah, they assist the trailing edge flaps in the landing run, give that much larger camber, lots more lift as the aircraft is flying a lot slower. And then when the aircraft has landed, they are going to help increase the drag on the aeroplane, along with your spoilers and all the flaps dropping down. That's going to shorten the landing run. The more we do that, the more aircraft we can squeeze in and the more money we make. And money makes the world go around, so I'm told. Your leading edge flaps, 2 positions, extended and retracted, and that applies to the Kruger flaps and the variable camber flaps as well. Another example of your high lift devices, yeah, just showing how much more camber they can add to the wing. I don't know whether any of you guys have watched these things. Again, YouTube, it's a wonderful place. But these little aeroplanes can take off probably in the length of that classroom that you've got at NAT. Yeah, and they can land in that distance as well. They're absolutely phenomenal. Yeah, your lift dumpers, yeah, they are there. Your ground spoilers, assisted by the flight spoilers, deploy to the full extent to dump your lift. Your speed brakes, the spoilers are going to deploy within the specified range for the speed the aircraft's doing, and slow the aeroplane down in flight. Yeah, so as we're flying up for Dubai and we start to descend towards Kathmandu, yeah, we need to slow the aircraft down, so the spoilers will deploy a little bit. Pilot will select the flight day tent, or the range to the flight day tent. Yeah, the spoilers will lift a little bit. That'll slow the aircraft down. We can pop them up a bit more and a bit more till we slide into the flight day tent, and the spoilers are at the fully selected position. That's going to slow the aircraft right down. And that combined with the flaps, yeah, put the flaps down, that's going to give us lift at lower speeds. Aircraft plops onto the ground, and then all of the flight spoilers will go to their full extent, and the ground spoilers will deploy as well. That will dump all the lift over the wing. That allied to the flaps dropping down to their full extent creates an awful lot of drag, puts all the weight of the aircraft onto the wheels. So we get improved braking, we get improved steering, and we reduce the chances of aquaplaning. Ta-da! Yeah. Again, I won't go too deep this afternoon. I know it's Friday, and we're going to cover the levers, how the things are operated, all the rest of it. So don't worry about that just yet. There are 2 types of control system. We've got the manually operated control systems and the power operated control systems. Manually operated control systems running off control cables or control rods. The cable systems, the primary flight controls, your ailerons, your elevators, your rudder. Yeah, primary control surface moved manually by cables, pulleys, push-pull tubes, that sort of thing, or a combination thereof. All movements of the cockpit controls are instinctive, so if I push the stick forward, the nose is going to go down, pull the stick back, the nose is going to come up, turn left, turn right, roll left, roll right. Yeah. All the controls are duplicated, yeah, because in aircraft that are built to CS25 requirements, it's a part of the certification specification. It's a requirement that safe flight and landing is possible following a control jam or a severance of the controls. The jam is where something is wedged into the control run and preventing it from moving. A severance is where one of the cables has been it's come adrift, it's come out of the system. So the requirement is normally met by duplicating the aileron and elevator control runs and providing a disconnect unit for them. So that then will allow the pilot and the co-pilot's controls to be disconnected from each other should we get a jam. Yeah, the pilot's controls operate the left-hand side, co-pilot's controls operate the right-hand side. Normally they'll be interconnected, so it doesn't matter who's got control, But in the event of a jam or a severance, the pilot will look after the left-hand side, the co-pilot the right-hand side. We separate the two runs by running them along each side of the fuselage. Yeah, so that's your control cables. Yeah, coming from the right-hand side. The same will be duplicated on the left-hand side, and the two of them will be interconnected. What have we got in the system? Stuff that we should have come across previously. The control cables made from galvanized carbon steel or corrosion-resistant steel. And those cables have got appropriate end fittings put on them for connecting them into the system. Turnbuckles are fitted in the system so that the control cable tension can be adjusted. Yeah, and there are different types of turnbuckle. You've got your American one, you've got your brass one, the different types of locking. I think the British one's got the locking nuts at the end. The American ones have got the locking clip down them. So it just depends on the type of cable you've got as to the type of turnbuckle. And then, of course, your ends fit in switched onto the end of the cable so you can connect them into wherever they need to be. Fair leads are fitted to give the cables a nice clear run to avoid fouling and chafing. And the fair leads, as we know, are made from Tufnell and just allow the cables to transit through them. Your pulleys are there to change the direction of the control run. Yeah. Fair lead must not deflect the cable more than 3 degrees. That's down on page 12 in the fair lead and pulleys bit. Yeah, I don't think it comes up as part of Mod 11, but just be aware that a fair lead is just there to guide the cable, keep it out of mischief. The fair lead isn't there to change direction. So that 3 degrees is the maximum a fair lead should deflect a cable. If we want to change direction, then we're going to use pulleys. Yeah, the pulleys, cable goes round them. They've got guards on them to prevent the cable coming off. Pressurized bulkheads, yeah, we're going to have seals that the cable passes through just to prevent a loss of pressure as we go from a pressurized area to the non-pressurized area. Chains, we might find chains in the system, chains driving from the control wheel down to the torque tube, for example. Chains found in control columns, trim systems. We can use them with our cables, no problem there. As we said before, what I will explain now is in the notes, they are showing all the different devices that we can use to fulfill the functions that we require. You're not going to get all the devices on one aeroplane. Yeah, they are going to be, the notes are just showing all the different types of device we can get. But if we tried to put them separately, the book would be about 4,000 pages long. So the examples that you get, you might not see every type on one aeroplane, if you see what I mean. Right. So the aileron and elevator. Yeah. The ailerons are operated from the hand wheel. Yeah, and the hand wheel moves left and right. Hand wheel left and right, and that's going to drive cables up to the ailerons. If we get a jam in the system, yeah, it's the natural thing is if you've got a blockage, if you've got a jam, is to try and overcome it. Use brute force to try and overcome that jam. The way we can provide our protection against that jam to separate the two systems is by using what they call a D10 strut, sometimes called a crush strut. Yeah, If, let's just say, the pilot has got a jam in his system, he's trying to overcome it, he forces the hand wheel round, and forcing the hand wheel round causes this interconnecting strut to collapse on this side. The ones I've come across, basically, it's like a foil inside, and that foil, under normal circumstances, will take the normal loads that a pilot is going to input into it. If there's too high a load put on, yeah, the foil collapses, it just crushes. So you get what they call lost motion. So now the right hand side, the co-pilot, he's got control of the ailerons from his side. If we get a severance in the system, yeah, let's say again, I don't know, Prakesh has gone mad with a set of scissors and he's cut the cables on the left hand side. What we want to do is separate the left hand from the right hand side, so there's a disconnect handle. Yeah, the pilot can pull the disconnect handle, and that will create a break between the left hand and the right hand side. And again, now the co-pilot can continue to control the aeroplane. If he pulls the disconnect handle, he'll get a warning to say that the thing has been activated, that the ailerons are uncoupled. The elevator, same sort of thing. The stick goes backwards and forwards to control via a torque tube. Calls it a lay shaft there, but via a torque tube to control the elevators. Yeah, the elevators are a one-piece control surface at the back. Yeah, the cable's connected to the left and the right side of the elevator, so it doesn't matter what the pilot or the co-pilot does, the elevators are going to respond. However, if we get a jam, yeah, again, let's say the pilot side is jammed, he's going to try pulling back on the stick, and pulling back on the stick is going to activate the disconnect device. Disconnect device will operate and it will segregate the left hand from the right hand side. So now this side, any inputs are going to go off to the elevator and carry on using them. Again, we've got a manual disconnect. So if we've got a severance, for example, there's a manual disconnect facility. And again, if we activate that, there's going to be a warning light in the cabin. Ta-da! Yeah, that's just showing us how the control wheels convert in linear movement. Yeah, the rotary movement, sorry, converted to linear movement. And we're just going to use a little chain wrapped around the top of the handle, and that's going to be connected to a sprocket. Push-pull rod, we've got a torque tube there that's going to rotate should we need it to. Not a lot else to say there, quite honestly. Yeah, so we've got the protection against jam, we've got the protection against severance, and while you're disconnected, you've got the indicator as well. Ting, ting, ting. Right, your manual systems then.
Jim.
Yeah.
When there is jam, there is no indication in CWP. Jam disconnection.
No, it's when the pilot pulls out the disconnect that the indicator comes on. Is jam indication is him going to be trying to move the control column or the control handle or the control wheel, and he's going to have that resistance to it. That's his indication that he's got a control jam.
And the jam and severance, both similar terminology?
No, a jam is where something is blocking the. Let's have a look. Right, if that's a control bracket, yeah. Forget that. A jam is where something is stopping the controls from moving. So matey boy here, somewhere in his mechanism, if we've left a screwdriver in there and the screwdriver is preventing the controls from moving, that would be a jam. The controls are jammed. A severance is where there's a separation of the control cable, whether it's been cut through by chafing or whether a bolt's come out and the cables come adrift. That would be a severance. Yeah. So where a cable or a component comes away, yeah, and stops the system from working, that's a severance. Where something is blocking the operation, that is a jam.
Okay.
All right.
In order to overcome both of this situation, in aileron we disconnect interconnecting mechanism.
Not both.
No. In aileron we do the interconnected mechanism, and an elevator we get it through the spring-loaded dog clutch.
No, if you've got right, let's say you've been working in the cockpit and you left a screwdriver lying around. That's a screwdriver, and that screwdriver is stopping the control from working. Yeah, it's stuck in the pulley. Now the pilot is going to try to move the control column, yeah, and he can't because that screwdriver is stopping him from moving anything. The more force he applies, yeah, that what they call the D10 strut is going to collapse. Internally, what you've got, if that's your D10 strut, inside it's filled with a sort of foil. Yeah, and your control input, there's a piston on this side, and as the let's just do it that way. Yeah, if you imagine that's your D10 strut. So from your handle, your control column, you move left and right, and this little piston will move left and right. And it'll carry the D10 strut with it, and everything will be happy. If I get a jam, I'm going to put a lot of force onto the stick to try and overcome that jam. And what happens as I do, the little piston in the D10 strut crushes the foil or the honeycomb inside it, causes it to collapse. So now when I move the stick, yeah, this piston is just moving in free air. It's not moving the control for the other side. So the controls have effectively become separated. Now the co-pilot has got control of the ailerons. Yeah, so him moving the stick, he is moving the ailerons. This side, if I try to move the stick, nothing's happening because the inside of this has collapsed. So I've just got free motion here. It's not affecting the controls whatsoever. So that would be my protection against a jam.
Okay.
Yeah, you with me there?
Yeah.
A severance. Yeah. Let's say we have a severance and we'll say Yadav because I know his name. Yadav's gone mad with a big pair of shears and he's cut the cables on this side. So now the cables aren't connected to anything. Yeah. It doesn't matter what the pilot does or the co-pilot does now. This side, the cables are just flopping around free. So to isolate them from the system, what we do is we pull the disconnect handle, and by pulling the disconnect handle, it separates the left hand from the right hand side. So now it doesn't matter what the pilot does, all that is immaterial. The co-pilot has got full control of the ailerons from there. You okay with that?
Yes. And in case of aileron?
The elevator, that is the ailerons.
Yeah, I got
the elevator.
Yeah,
It's exactly the same principle.
Okay,
if
I got.
we have a severance, yeah. Again, Yadav he's having a field day with his scissors. He's cut the cables. What we do is pull the disconnect handle, yeah, and that will separate the left hand from the right hand side. If we get a jam, yeah, somewhere down the line, yeah, our screwdriver again, for example, somewhere down the line, we've got a jam in the controls. What happens is as the pilot is trying to turn the push and pull forward on the control column, it causes this disconnect device to activate, and that separates the two halves of the controls. So now the co-pilot has got full control. Yeah.
Okay, Jim. Thank you. I got. Yeah. Thank you so much.
That's okay. Well, we'll have a look at how they operate in a minute anyway. But that's that. Yeah. Early days of flying. That was them going off for a nice Sunday afternoon flight. Yeah. He looks absolutely barking, doesn't he? Barking mad. He looks like a serial killer. And she just hasn't got a clue what's going on.
Just behind
Right, so your manually operated ailerons, yeah? And again, it's highlighting the fact that ailerons provide rolling control about the longitudinal axis. The ailerons themselves hinge to the trailing edge of the wings, normally out near the wingtips, yeah, to give us the best turning moment that we can. The controls operated from the control wheels mounted on top of the control column in the flight deck. Control wheel to turn clockwise, anti-clockwise. The ailerons are going to move correspondingly, as we saw in our theory lesson. Yeah, if I move the control wheel to the right, the right aileron moves up. If I move the control wheel anti-clockwise, the left aileron moves up. And the opposite aileron the opposite way. Yeah, converting the rotary motion of the control wheel. Different ways of doing it. In this one, it's just showing a cable, or is it a push-pull rod with a chain on the top. So as I turn the handle, the little sprocket is driving the chain, and that in turn is attached to a chain at the bottom. And again, that's going to provide our turning motion, and that is then going to be translated into linear motion at a bell crank. Ta-da! Yeah, so chain, sprocket, yeah, bell crank at the bottom. So as I move the gears left and right via that little bell crank, what I'm doing now is moving the cables fore and aft. What they call the bus force limiter here is exactly the same as I was saying. It performs the function of disconnecting the left hand and the right hand side in the event of a jam. They just call it a force limiter assembly on this particular drawing. So don't let that fool you. Yeah, and then via cables and pulleys and all the rest of it, our left and right motion is being transferred to the ailerons. Because you've got that interconnect, if I move the left hand wheel left and right, then the right hand wheel is going to move left and right, and vice versa. If the left hand wheel moves, the right hand wheel will move. Yeah, so different ways of converting that motion, and it just describes those. Again, we won't worry too much about that. Yeah, nothing there for us to worry about. Cables tensioned by turnbuckles, and that tension is checked with a tensiometer, or some aircraft have got a tensioning device in them. And just some nice pictures and some more pictures. And there's your ailerons. Yeah, ailerons at the back of the wing. Right. We talked about the left-hand wheel driving the left-hand aileron, right-hand wheel driving the right-hand aileron, and that's tickety-boo. If you got to a situation like this where you lost an aileron, you're not going to lose the aeroplane, because so long as your other aileron is controllable, whatever happening at this wing, the opposite's going to happen at this wing. So if an aileron comes off for whatever reason, at least the pilot has got a modicum of control to try and get his aircraft back down safely. The control won't be fantastic, but there will be a little bit there. Boom. And that's your typical cable control system. Left-hand side, right-hand side, D10 strut interconnecting via your pulleys, cables for tensioning, yeah, and off round to our ailerons. Yeah. One we'll come on to in a little while. We've got an input for autopilot in there. Yeah, we've got our disconnect device, so if we get the jam, we can disconnect the two sides, and then in this one, the set of cables just interconnecting the two systems. Again, we'll look at that in a bit more detail. Yeah, and again, your cables connected to the aileron. In this case, this particular one, it's showing a servo tab, so the cables will be driving the servo tab, which in turn will move the aileron for us. But just the general layout: turnbuckles, pulleys, hand wheel, interconnect, disconnect. Ta-da. Everybody okay with that?
Jim.
Yeah.
Is this D10 strut and boss force limiter assembly, is this same unit with different terminology, or they have different?
Yes, that's what I was saying. It's exactly the same thing. Okay. It's performing the same function. Okay. Yeah, it might be slightly different internally, but it's performing the same function.
Thank you, Jim.
Okay. Anyone else? Right, page 21, again, worth a highlighter. It's something that we have mentioned before, but it does come up. The fact that the ailerons operate in such a way that the down travel of the downgoing aileron, the down travel is less than the up travel. That reduces the aileron drag and reduces the possibility of tip stall when we're carrying out low speed turns. Yeah. So that differential aileron, yeah, how we're going to achieve it, and it's basic geometry that we use, yeah. So the cable quadrant, yeah, cable quadrant attached to a lever, the lever attached to the aileron, and it's the movement of the lever, yeah, and the distance the lever travels that is determining how much movement we get at the aileron. So as I move the aileron up, yeah, I'm getting a large degree of movement. Yeah, if I move the aileron down, yeah, I'm getting a smaller degree of movement. That's how we're going to get our differential aileron. Yeah, so although we've got the quadrant, pulley, if you like, we've got the lever in the middle of it. Yeah, although we've got a travel of equal arcs, yeah, the up movement and the down movement are going to be different. Yeah, and that is what gives us our differential aileron. Another method, and probably an easier method of seeing it, is the bell cranks. Yeah, the offset bell cranks that are attached to the aileron. So as I put an input to the clockwise input into the aileron, yeah, that bell crank on this side is moving to give me which one we're going, small degree of movement, yeah, and the other one's giving me a larger degree of movement. So although the bell cranks are shifting, the difference in movement at the ailerons is quite marked, and obviously it's going to work the same in the opposite direction. Yeah, so as I turn the control wheel that way, the bell crank lever is going to move. Yeah, as the bell crank lever moves, because of the angling on it, yeah, I'm getting a small degree of movement on the down going aileron. I'm getting a larger movement on the upgoing aileron, and that's how our differential is being achieved. Yeah, yeah, it just describes the operation on the bottom of page 21. But the idea is, and the bit that we need to worry about is we're going to get more movement on the upgoing than we are on the downgoing. Yeah. And again, they're going to show you the schematic of the bell crank. Yeah. Just a general layout. Yeah, we've got our hand wheels. Yeah, the tension regulator that's keeping the cable tension going. We've got our drive down to our control rods, and between the two, we've got the disconnect unit. At the front end, you'd have your D10, not D10, your interconnecting lever. So your disconnect unit, yeah, allows us to separate the two. Down to the ailerons, yeah, we'll look at trim in a little while. So we're going to have a trim facility for our ailerons, and in this case we've got servo tabs fitted on the ailerons. The servo tabs giving us that aerodynamic movement of the control surface that we talked about yesterday. Come on to that in a minute. Yeah. Ding, ding. Nothing else I can see there. Sorry, I'm just flicking through to make sure that I've not missed anything. Schematic of the aileron system. We've just seen that linkage from the control wheels to the ailerons by arrangement of pulleys, cables, and quadrants. Push tubes and bell cranks. Don't worry about the degrees of movement of the ailerons, but just know that the upper limit is bigger than the lower limit. Captain's first officers runs joined by the disconnect unit, and the unit allows the two runs to be separated if we get a jam. Yeah. Again, if we've got an interconnect rod at the front end, we might not have the disconnect unit at the back end. Yeah, as I said, the notes tend to cover all the different devices that we might use. So don't expect to see a crush strut at the front and a disconnect device at the back on all aircraft. It'll vary from aeroplane to aeroplane. But this is just to give you an idea of what the things are about and how they're working. Trimming provided by a trim tab or a servo tab on the ailerons in the example given. Tab driven by electric actuator. Tab functions as a servo tab to give aerodynamic assistance to the roll. Yada yada. Nothing we need to worry about there. It just tells us how the control cables are routed down the left hand and the right hand side. We've talked about that. Joined by the interconnect rod, and it's showing a disconnect unit in the trailing edge as well. Yeah, normal circumstances, the movement of one control wheel moves both ailerons and the other control wheel. Should one become jammed, yeah, the two are separated by the application of a higher than normal force to the control wheel, which was the the interconnect tube that we've just been talking about, or the bus force limiter as it describes it on that particular drawing. Normal operating conditions, 2 halves of the unit are firmly engaged and move together as a single unit. Should one side jam, the 2 halves disconnected by application of the higher than normal force at the control wheel. Yeah. We'll separate the two. Disconnect switch, yeah, I'll come on to that in just a minute. It performs the same function. It's separating the two sides from each other. The quadrant is just what we're going to use to give us the movement. Control rods, we should know what control rods are. And aileron position transmitter provided so that the pilot can see what position his aileron's in. Especially useful if he's got trim applied. Yeah, you can see what the position of his things are. Oh, thank you. However, let the man in. Yeah, and that was the thing we were looking at. Yeah, the disconnect unit, the interconnect, servo actuator for putting trim inputs in, the trim coming from electric trim motor in this case, trim actuator driving the trim tab, and there's a servo tab as well for that aerodynamic assistance. Ta-da! Right, disconnect unit. Yeah. Again, this instance, yeah, we're showing we've got a disconnect unit. The disconnect unit, as the name suggests, is going to disconnect the left hand and the right hand side from each other. So you've got a rod from your right hand control, you've got an interconnect rod from the left hand side. And while that unit is operating, yeah, it doesn't matter which side your input comes from, the opposite side is going to feel that movement. Yeah, the autopilot actuator we'll look at in a minute. Little electric motor in this case, and that's just via a cable putting an input into the quadrant. So if the autopilot says move, it'll move the quadrant, and that will put in the input to the ailerons. Yeah, so your autopilot quadrant there, a little torque tube, your control rods from the left hand side, the interconnect, the right hand side, all receiving the same inputs. Yeah, from your cabin, yeah, from the hand wheel, again, those inputs are going into the quadrant, and again being transferred to the other side. The disconnect unit, as we said, the right hand side and the left hand side, and the two halves of the unit are held together. It's a bit like and the one time you need one, you haven't got one. If you can imagine a jam jar. Can you see my happy face on the screen? Yeah, if I've got a jam jar and I've got a lid on the jam jar, if I turn the jam jar, the lid's going to turn with it. If I want to take the lid off, I'm going to twist the lid. Yeah, and it's going to separate from the jam jar. It's the same sort of thing with our disconnect unit. The disconnect unit is two halves held together, and normally they will rotate together quite happily. So if I put an input in from the left hand side, input from the right hand side, whichever, the whole unit's going to turn. If I get a jam, yeah, and I apply too much force, then which side I'm applying the force to is going to separate the two halves of the disconnect unit. So now that half is going to rotate independent of that half. So I'm separating the two the two halves of the system. Does that make sense? I'll take that as a no then.
No, we are getting.
Yeah, we got it.
Yeah, you're getting it. Okay, so lovely. So if I've got a jam in the left-hand side, yeah, I'm trying to force that rod. It's going to cause the two halves to ride apart from each other and disconnect the left-hand side from the right-hand side. That's your disconnect unit. Yeah, it's a disconnect unit there. Interconnect rod, yeah, and then this is going to put inputs in via a quadrant into the left-hand side, yeah, and again via push-pull rods and just little levers, we can transfer that motion down to the ailerons, yeah, via your little drive rod there, and that was your basic aileron system. Has anybody got any problems with that? Have I explained that okay? There shouldn't be any problem. It's all fairly...
Excuse me, Jim.
Yeah.
That disconnect will disconnect from the control column, or we have to move something?
No, it'll disconnect the left-hand side from the right-hand side.
But how?
So a bit like that interconnecting rod that we saw. Yeah, yes. The interconnecting rod is going to separate the left-hand side from the right-hand side. The disconnect unit does exactly the same thing.
But
so in the event of a jam, it'll cause the two sides to... Sorry?
We have to apply the force for disconnect.
Yes, if you've got a jam in the system, it's human nature. You're going to try to apply more force. And by applying more force... that's going to cause the disconnect unit to disconnect, and it will separate the right-hand side from the left-hand side.
What in practical we have seen in the aircraft is given the T handle to disconnect.
Given the what?
Given T handle to disconnect the controls. Disconnect controls. If we have a jam, we can pull the T handle, then we can disconnect the controls.
Yeah, but pulling the handle is normally for a severance.
Yes. Okay.
Right.
For severance only. Okay, I got it.
Normally. What it's saying in for the ailerons? Somebody got the mic on. Yeah, the D10 strut is joining the two control columns together. Yeah, so if I get a jam up here, yeah, I'm going to sense that at my handle. I'm going to force the handle. It's just human nature to force it. And what's going to happen? That D10 strut is going to separate the left hand and the right hand side. So now I've taken this out of the game. All my control for the ailerons is going to be via the left-hand side. Yeah. Because we've got these from here, yeah, we've got these interconnects. Yeah. So the interconnect cables are joining the left-hand and the right-hand side. Yeah. So any inputs here will be felt at both ailerons. Yeah, so both sides are interconnected. The disconnect device, again, if I feel a jam, yeah, so let's just for argument's sake, yeah, I get a jam here, yeah, as the pilot's inputs are going, yeah, it might not be felt there, but the disconnect device will operate, and the disconnect device operating will again separate the left-hand side from the right-hand side. So because the disconnects are activated, the pilot's got no input, but the co-pilot has. So the co-pilot will be operating his aileron. Whatever happens at this one is going to happen at this one. Yeah. So we're disconnecting the two halves of the system. If I get a severance, yeah, a severance is where we said Yadav, didn't we? Yadav's gone mad, and he's cut through the cables with a big pair of scissors. As his scissors, yeah, he's cut the cables. So now the two systems are separated. There's normally a disconnect handle somewhere. Yeah. So what can happen is the pilot will pull the pin, and that will disconnect the left hand and the right hand side. So again, this side has got primacy. This side is controlling the ailerons. Yeah, this handle's got no input in it because they're running down the different sides of the aeroplane. The protection is by duplication. Like I said, as I did try to say, you know, you might not find all these features on every aeroplane. You might get a mixture of them. You might just get one type. Some aircraft you don't have the disconnect handle. The disconnect device operating will put a light on in the cabin. Yeah, so it kind of just depends on the aircraft type, how many of these features, if any, you get on your aeroplane. Okay with that? Has that answered your question?
Yes, sir. Okay. Thank you.
Yeah. Okay. Right. A quick look at the elevators, and then we'll have a quick break. Yeah, so your differential ailerons, yeah, we did that through geometry. Yeah, I had a look at the different things. The disconnect device separating the two halves of the system. Yeah, and it just works like rides up on a cam, and the two halves are separated. Elevators, yeah. Elevators, yeah, we're in this system. We've got the control column, yeah, and again, as we push the control column backwards and forwards, that's going to put an input into the elevators. The elevators, one piece control. Well, they're two pieces, but they're interconnected by a physical torque tube. The elevator runs joined by the disconnect unit. And that allows the two control runs to be separated in the event of a jam. Yeah, severance is protected against because the two different halves are duplicated. Yeah, so again, backwards and forwards, pulleys, yeah, cables, not tensiometers, turnbuckles. Yeah. Down to the torque tube there, and the torque tube via your levers, putting inputs into the elevator. Yeah, you can see two halves of the elevator are joined physically by a torque tube. So if I disconnect one half of the left-hand side, the right-hand side will still operate, and it'll operate both elevators. Likewise, if the right-hand side, for whatever reason, is disconnected, then the left-hand will still operate the elevators. If I get a jam, there's a disconnect device in there, and if I get a severance, I've still got authority over the elevators. Okay with that? Yeah. Simple, straightforward. What I want to do, I think we come on to it a bit later as well, but we want to limit the amount of movement that we are giving our ailerons, that we are giving our elevator that we're giving our rudder. Because if we give it too much movement, we'll get too much stress on the airframe. The aircraft could over-maneuver and we could get into quite a dangerous situation. So what we do is we put stops at the control column end of the system and at the flying control end of the system. Yeah, and the stops are adjusted to limit the amount of movement that we get eventually at the control surface. The rudder, the rudder is operated by pedals on the floor of the aircraft. Pushing the pedals left and right is going to operate the rudder left and right. Again, we've got duplication as our protection. So we've got a better picture. Yeah, so from your rudder pedals one side, running down one half of the aeroplane, we've got an input up to the rudder, and we're going to have duplication down the other side up to an input to the rudder. Rudder provides directional control about the normal or the vertical axis. Hinged to the trailing edge of the fin, we should know that. Operated by rudder pedals, pilot's got a set and the co-pilot's got a set. Pushing the right pedal, rudder moves to the right, aircraft will move the right, left pedal, vicky-verky. Interconnection bar between the pedals, and the bar adjustable for the length of the leg of whoever's flying. If you've got a dwarf flying, obviously his feet won't reach, so he needs to move the pedals forward so he can reach them. Limiting rudder deflection at higher speeds, we talked about that, and we'll have a look at that. What we're going to do is reduce the rudder movement the faster the aircraft's going. And again, that is protecting the structure. The rudder may incorporate a spring tab to assist the pilot in moving the rudder at lower speeds. However, the action of the tab is inhibited at higher speeds because the airflow at high speeds holds the spring tab in neutral anyway. Rudder pedals connected directly to the rudder at higher speed, pilot gets no assistance. So again, because he's getting no assistance, that's limiting the amount of movement he can give to the rudder. Rudders incorporate electrical or manually operated trim tabs, and that trims the aircraft. Don't forget, trimming is to correct for a flying fault. Ding. Autopilot. We can have autopilot inputs into the rudder from an autopilot actuator. Typical rudder system. Your pedals, your left and right. We can move the pedals backwards and forwards depending on the length of leg. We've got an interconnect between the two. Then from the pedals, again via your push-pull rods, bell cranks, and I think there's a torque tube in there. The input to the rudder. Duplicated as we come down. Again, we're going via quadrant. Push-pull rods to the rudder itself for moving it. The spring tab in there. We've just been through the spring tab. Spring tab to give assistance at higher speeds, at low speeds. Sorry, at higher speeds, the airflow will tend to push that back into a neutral position. So the pilot's just got to rely on his feet. And just by him relying on his feet, the strength, the force he needs gives us that limiting effect. And again, just the typical rudder trim system. Let's see what we say on that one. There is a bit about the duplicated link there. I'll come on to that in just a minute. The duplicated link. The reason for that, if I remember rightly, what's happening with the duplicated link? If we only had one and it broke, then the tab would start to flutter. And if the tab was fluttering, that would be felt by the rudder, and the rudder would start fluttering. And that would create great oscillations in the aircraft. It'd be swaying backwards and forwards. So they duplicate the link in case there's a failure. Autopilot. Yeah, it talks about autopilot next. The autopilot inputs. Yeah, the autopilot is going to feed in any changes in direction, any alteration of the flying controls via a little electric motor, basically. The autopilot servo is taking an input from the autopilot system. The autopilot system is just driving a little motor, which in turn is moving a lever. Connected to the lever is a little rod, and as that little rod moves, it's causing the input cable to the control system to move accordingly. Yeah, so the reversible electric motor, well, that means it'll go both ways. Moves the lever, operates a cable via a drum or push-pull tube. Cable drum forms part of the primary control system. The autopilot servo runs in whichever direction. Yeah, and the input is fed into the primary system. Yabba dabba do. Right, that I think is a good place to stop and have a break. 14:25. We'll have a 15-minute break there because I'm parched and I need a cup of tea. So we'll have 15 minutes. Cup of tea, stretch of the legs, run around the block, and then we'll finish off these initial bits of the flying controls that we need to look at. Okay with that? Has anybody got any questions before we do? No? Okay then. Right, I'll see you in a few minutes then, guys.
Okay, sir.
Okay, everybody back? So that was a yes. Right. Next bit that we need to look at then. Ting, 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 ting. What's going on here? Yeah. Gust locks and gust dampers. Gust locks and dampers. Why are you in there? Gust locks, gust dampers. Sorry, I've just got a weird screen coming at me for your class meeting. That's it, sorted. Right, gust locks, gust dampers. What we're trying to do with these things is protect the control surfaces when the aircraft's parked outside. What we don't want is the wind to be blowing the controls about backwards and forwards, bashing the controls against the stops and causing damage. So again, it's kind of aircraft type dependent on how we're going to lock the controls. Some aircraft have got a pin that we can place into the control system in the cabin. Other aircraft, it's a lever that we operate, and the lever just drops drops a pin into the control system. So this sort of thing, control locks, just pretty much like a rigging pin. We put the control column in a neutral position, both fore and aft and left and right, and drop the pin through, and dropping the pin through will lock the controls. The rudder pedals have got something similar. We just pull a little lever and that locks them in the neutral position. The gust locks should have some means of preventing us from taking the aircraft off, getting airborne with the things engaged. The internal type, if we've got a smaller aircraft, we don't have the Gucci pins or anything, what we could do is have external locks, and the external locks just fit in between the structure and the control surface, and pretty much wedge them in position. The reason you've got this particular picture, the control lock in this case is exactly the same color as the aeroplane, and there's no warning pennant fitted, so it's to highlight the fact how easy would it be to take the aircraft off with that lock fitted, and if the pilot didn't know, tries to operate his rudder, it could prove fatal. So your external locks, whatever the external lock is, must have some means of highlighting the fact that the lock's fitted. The ones in the cabin, again, there should be some sort of warning pennant or a placard or something that's going to get the pilot's attention to make sure that he removes the things before he goes flying. Again, my favourite YouTube, there's a film on there. It's only about 15-20 seconds, but it was a Caribou aircraft. The Caribou had been undergoing maintenance. They pulled it out of the hangar and everybody was happy. It was a older type aircraft, and the thing took off, flew in a great big loop and flew straight into the ground. And the board of inquiry that was convened, the investigation, found out that the control locks were still fitted. They hadn't been disconnected, and he just took off. His controls were jammed, locked in place, and nothing he could do about it. So that's your control locks. Your gust dampers are there to provide a similar sort of effect. They hold the control surfaces in neutral when the aircraft's parked in gusty conditions. Gusty, just blasts of wind. Engaged and disengaged by lever in the cabin. Lever operates a plunger, engages a control quadrant, and just takes the gust damper out of the system. Sorry, get myself confused here. The control locks, the lever operates a plunger, engages in the control system, so the control locks is putting a pin in. The gust dampers, again doing the same sort of thing. The gust dampers are there to prevent the wind, the gusts of wind, from pushing the control surfaces hard into the stops. The damper, it's attached to the rear spar of the main surface of the aircraft and the front spar of the control surface. It stops the wind blowing the control surfaces about, but it doesn't affect the operation of the control surfaces in flight. They're a fairly simple, fairly straightforward thing. Just a little reservoir, and the reservoir is feeding fluid to both sides of a piston. The ram on the control surface, the body on the aircraft structure. If the control surface tries to move, it's going to move the ram. As the ram moves, it's passing fluid from one side to the other via a little restrictor. And the restrictors there just to slow down the movement of the damper. Yeah. As I say, it's not going to have any effect on normal operations, but if the wind's trying to blow it, it's just going to restrict the movement. The piston is there, that top piston in the reservoir, just to make sure that there's a head of pressure in the damper, so we're not going to get any air in there in the event of leaks or anything. Yeah, so just the piston moving backwards and forwards, just passing fluid from one side to the other. If we do get a little leak, yeah, there's fluid under a small amount of pressure being fed to the ram. If we do get a leak, we're going to see it. We're going to see it at some point. Anything else I need to say there? No, I don't think so. That was the YouTube clip where it doesn't run. And control stops. We mentioned the control stops earlier. Yeah, the range of movement of the control surface gives us sufficient range of movement of the control without overstressing the aircraft structure or the surface itself. Yeah, so the movement limited. Setting it all up is going to be strictly in accordance with the AMM, but we're going to have mechanical stops in there, which we're going to adjust to make sure that we don't exceed that range of movement. Right, the stops are going to be located on or near to the cabin controls at the control column. Yeah, and the stops, the movement we input, the stops are physically going to prevent us moving any further. We're going to have one set of stops at the control surface and one set of stops in the cabin. Right. TDAR. What page am I on? I'm on page 38. And on page 38, please stick your highlighter through the fact that cable operated systems have two sets of stops. Yeah. The primary stops, yeah, are adjacent to the control surface. The secondary stops are at the cabin end. Yeah. So depending on whether it's a cable or a push-pull rod system, depends which are defined as the primary stops. So the primary stops at the control surface, they're the first ones to make contact. The secondary stops at the control column end, yeah, secondary stops have a certain amount of clearance. So when the primary stops are in contact, there's a bit of clearance for the secondary stops. And if we over travel, the secondary stops are there to prevent any further movement. If you've got a push-pull system, yeah, the control rods, push-pull systems, the primary stops are at the control column, and the secondary stops are at the control surface. So if you remember one, the other is the opposite. Yeah, your control cables, the primary stops at the surface, and the secondary stops at the control column. The push-pull ones are the other way around. So just remember one set, and you know that the others are the exact opposite. An example of your stop bolts, yeah. Limiting the movement of the control surface, so we're not overstressing that or the aeroplane. Anybody got any questions there? Anybody alive out there?
Live.
Yes, sir.
Yeah, you're alive. Woohoo! Don't worry, we're nearly there, guys. We're nearly there. I know it's been a long slog. Indications, warnings for your system. It says more modern aircraft. Signals from the control system sent to show us position of the control surfaces. We're going to get whether the controls have been disconnected, whether the disconnect units by been activated. And if we haven't got an ACAS, we're still going to get a CWP message telling us that we've got a problem. So that's your indications. Again, we don't need to worry about that. Everybody okay with that? Brilliant. Right, trim. Yeah, the next bit is trimming systems. And again, as we've said a couple of times, so we should be familiar, trim tabs are there to provide, to correct flying faults. Yeah. Flying fault, the tendency of the aircraft to yaw, nose or tail heavy, one wing low, and the various reasons we might get flying faults. Changes in weight, CG, passengers moving about, loading of cargo, asymmetric power. De-icing boots is always a favourite one. So any of those problems can cause a flying fault. And the trim tab is there to set the control surface so that the pilot can fly along without having to put a manual input in. The last thing he wants to be doing is trying to hold onto the controls for a couple of hours to keep the aircraft straight and level. Yeah, so tabs set to allow the pilot to fly hands off. Two types, as we discussed yesterday, we know about the fixed trim tab. Yeah, metal plate riveted to the trailing edge of a control surface, adjusted by bending. Yeah. And the controllable trim tab. The controllable trim tab operated by hand wheels or by an electric motor activated from the cabin. Yeah, fixed tabs normally found on smaller aircraft, can only be adjusted when the aircraft's on the ground. So they're, as I said yesterday, they're a bit of a pain to set up. But once they're set, that's it. You can forget about them until the pilot complains that they're not doing the job properly, and then we might need just to adjust them again. The controllable tab, yeah, so your fixed tab, your controllable tab, hinged to the trailing edge of the control surface, operated by the pilot during flight, electrically or mechanically from the wee hand wheel. Anything else I need to say there? Yeah, fitted to the ailerons, elevators or rudder. The controllable tabs correct faults at all speeds. Wonderful. Don't forget the positioning of the hand wheels. They're in the natural position. But the bit there at the bottom of page 40, the maximum free play at the trailing edge of a trim tab should not exceed 2.5% of the tab average chord. So what we're saying there, with my little pen, yeah, if that's the control surface, yeah, that's the trim tab, the average chord of the trim tab. The movement at the trailing edge of the tab should be no more than 2.5% of that length. Yeah, so if your average chord's, let's say 100 millimeters, yeah, there should be no more than 2.5 millimeters play at the trailing edge. Yeah, and the reason for that is flutter. Yeah, if we allowed that trailing edge of that tab to flutter, because it's attached to the control surface is going to start fluttering, and that flutter is going to be felt through the whole aeroplane. Yeah, so 2.5% of the average chord of the tab. So as you can appreciate, it's not a great deal of play, and the reason for that to prevent our flutter setting in, and the flutter having a detrimental effect. Simple trim system, setting a trim tab. Simple mechanical system coming from the cockpit hand wheel. Trim one way or the other. This is a pitch trim elevator. So move the tab up or down, and we're just going via a little cable to a screw jack. Yeah, the screw jack operated by a little sprocket. Yeah, so from your cable, little chain running around the sprocket, and as we move the handle, sprocket turns, and it's going to drive the screw jack in or out, which in turn is just going to set the position of the trim tab. Dead simple, dead easy, simple system one. Again, what we can do is incorporate, if we wanted to, we could incorporate an electric motor. Yeah, so we've got the hand wheel. Yeah, the hand wheel's great, it's going to wind it in and out. But what we can do is put an electric trim switch in the system. The electric trim switch driving a little motor, and that motor again is just going to put an input into the cable, which again is just going to move the trim jack in or out. Hand wheel turns, whole chain cable assembly is operated, turns the screw jack, moves it in and out, results in the tab moving up and down. Put the electrics in, yabba dabba do. Stops incorporated in the system to limit your trim tab movement. Yeah, so we can't have too much trim tab movement. Turnbuckles for adjusting the cable tension, and next to the trim wheel there's going to be an indicator to tell us how much input we've got. Yeah, so pilot needs to know how much trim he's got applied. The aileron one, aileron trim system is showing. Let's just see if we can find that one. Yeah, that was the. Sorry, I'm just making sure again I've not missed anything. Right, your electrically operated trim system, that's just showing the aileron one. We've got the trim switches, left wing down, right wing down, what have you. Trim system has got to be protected from what they call a runaway actuator. So if the actuator starts to operate without a proper command, yeah, it can take the trim tab to its full extent, and that would make the aircraft quite difficult to control. So if we've got an electric trim circuit, we need to have two inputs. Yeah, we've got to have an armed command and a control command. Yeah, so arm switch, command switch, yeah, they're both supplying electric to the motor, yeah, but you've got to have both signals present before the actuator will run. Yeah, the switch is sprung loaded to the off position. Yeah, switch is released, earth placed on each supply line prevents a short circuit operating the motor. So with this one, yeah, if I'm flicking the toggle switch, it's not a fantastic drawing, I appreciate. But if I flick the toggle switch, yeah, I want to bring my right wing down. Yeah, I'm going to have a command signal in there and an armed signal. Yeah, both of those signals have got to be present before the trim actuator will move. Yeah, so if I'm going, just for argument's sake, I want to go left wing down. Yeah, left wing down signal. Yeah, sitting there ready and waiting. So now make my selection and the motor will run. but the motor can only run so long as I've got the armed switch in the right position as well. I think we come on to a better drawing of that, but you get the idea. On the bottom of page 41, if you remember that both switches have got to be in operation, yeah. So you've got to have an armed signal and a command signal before the motor will run. Aileron switches mounted on the center console, yeah. Elevator are mounted on the thumb position on the control wheel. When it talks about a split field motor for the trim actuator, all that means is it will run in 2 directions. It will go back and forth. Yeah, the split field motor. So what we're saying, we're taking our electric signal. Yeah, so long as you've got both signals present, yeah, we'll make our up selection. Yeah, we've got limit switches fitted in the system to prevent the actuator from over traveling. Yeah, so as we make our selection, let's say we're going to go down, yeah, through the actuator, the motor will start running, the thread will start running, the little lump will run. As soon as that limit switch is made, it'll cut off the supply. The other one will limit switch will make, so we've got a reverse selection. Anything else I need to say there? Not really. Yeah, during autoflight, yeah, the autopilot will keep the aircraft trimmed. That'll use the electric trim actuator. Rudder trim tabs, a rotary switch on the center console, a bit similar to our hand wheel, but just a flick left and right. Rotary switch, split field motor connected in there, and within the motor there's a solenoid brake as well. So when power's switched off, the brake will apply. When power's switched on, the brake will release to allow the motor to run. Yeah. So again, your limit switches on your actuator, your motor running. If I haven't got the power there, then the brake's applied. Nothing can move. Once I select power and make a selection, then the solenoid brake will release and allow the motor to run the actuator. So again, all designed to prevent any spurious trim inputs. La 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 la. And some nice pictures there as well. Yeah, again, we've seen those, we've seen those. Nothing there for you guys to worry about really on the notes. Yeah, yeah. The only bit, as I say, the bit about both signals, command signal and armed signal, both got to be present before the motors can run. Yeah, both switches. Normally they're under a common thumb point, but both switches operated together. Sprung loaded to the off position. Split field actuator, I've mentioned that. That's just makes the motor runs in 2 directions. And then there's about 3 pages of pictures that we've just seen, the manual and the electric input. Pictures of the trim wheels. Yeah, each of the trims going to have an indicator next to it. Yeah, and the trim with the duplicated linkage, that one has cropped up in the past. Just make a note of that the duplicated linkage is there to make sure that we don't get flutter if one of the link, if we just add one link. Tabs themselves, yeah, trim tab, as you can see on the slide, just a little hinge tab that will either protrude up or protrude down in the airflow, and it's going to position the control surface to keep us straight and level. It's going to correct for that flying fault, and that trim tab is going to stay in that position until it's otherwise selected. Yeah. Again, that's just straight from the notes, but coloured in. Yeah, your trim wheel for your ailerons. That will be your trim wheel for your rudder. Trim wheel for your elevators. Yeah, but as it is the aileron. Yeah, left or right. Again, putting an input in up to that little manual trim motor, trim actuator, and your linkage, and it's going to move the tab up or down. There you go, same sort of thing, but just showing there's an electric actuator in there. The electric actuator is just going to put your inputs in, and again the inputs to the tab. Yeah. Again, not a lot else to say on that one, quite frankly. Geared tabs, yeah, we looked at geared tabs and the fact that your geared tabs will give you balance and anti-balance. Balance tabs, aerodynamic assistance to the pilot. Yeah, could be fitted to the ailerons, could be fitted to the elevators, the rudder. And your balance tabs can act as trim tabs as well. Yeah. If it's set in the trim position, it will go back to the trim position. With a geared tab, it will act as a balance tab as we move the control surface. The geared tab, it will get to a certain point. It will become an anti-balance tab, resisting the movement of the pilot. Whichever way, yeah, the bit about tab operating linkages duplicated to prevent flutter that I was yapping on about before is on page 47. Page 47, second to last paragraph there. Tab operating linkages are duplicated to prevent flutter following a single linkage failure. Aircraft with powered controls that might have manual reversion. Again, with that type of aircraft, we may well put balance tabs on. We're going to look at power controls on Monday, but bear in mind, if we've got a manual reversion, obviously having a powered control means that the control surface is going to be hard to move anyway. So if we've got a manual reversion from a powered control system, we'll maybe give balance tabs to help the pilot move the control surfaces. Yeah, the geared balance tabs, allows the effect to be varied in proportion to the control surface deflection, and then when we get to a certain point, it'll kick over and it'll give the anti-balance. And again, that's to protect the aircraft from overstress. Yeah, so going from your neutral, we saw this yesterday. As I move the control surface, the tab's going to move to give me that assistance. I'll get to a certain point in the movement of the aileron, and the geared tab will kick over. The tab will move to resist the movement of the control surface, thereby protecting us from the pilot. Your balance panels, again, we looked at those yesterday. The balance panel is there again to help the pilot to move the control surface, and all it is as the name suggests, it's a panel in the back of the wing cavity attached to the control surface, in this case the aileron. As the pilot moves the aileron, it opens up it calls it a vent here, but it just opens up one surface to air pressure. The other one's closed off slightly, allows air in the lower chamber to escape. So as he tries to move the control surface, the higher pressure on one side of the panel is giving that aerodynamic assistance to move the control If he moves it the other way, the opposite effect. Yeah, one side is going to be reduced, the other increased, and again we're going to get higher pressure on the opposite side. Again, giving him that assistance to move the control surface. So we saw that yesterday. Our balance panels. Yeah, we just looked at that one on page 50. Servo tabs. Yeah, servo tabs connected directly to the pilot's controls because it takes less effort to move the servo tab than it does to move the control surface. Yeah, again, servo tabs fitted to any of the primary surfaces, and the illustration, the picture on the slide there, shows it fitted to an elevator. In this example, the elevator is moved not only directly by the control column, but by the servo tab as well, depending on the speed of the aircraft. Yeah, when control column's pulled back, linkage to the elevators moves via a pivoted crank. That's your little pivoted crank. Yeah. Which in turn moves the tab, assists the pilot to move the elevator. At low speeds, the aerodynamic loads are low. Large deflection of the elevators is required. The pawl on the follow-up crank reaches the stop. The pilot raises the elevator directly. Control column pushed forward. Second pawl contacts the stop. Elevators are lowered, again assisted by the servo tab. High speeds, aerodynamic loads are great. Smaller deflections of the elevators are required. The tab alone can move the elevator. So what we're doing with the servo tab there on the back of the elevator, and we've got this what they call a follow-up crank and a stop. Yeah. Input from the pilot via a push-pull rod, whichever way we're going. That input is going to move that stop. As it moves the stop, yeah, he's going to move the whole control surface, yeah. But at the same time, there's going to be an input to the tab. So as he moves the control surface, again, the little link rod via a little bell crank is moving the tab at the same time. Higher speeds, yeah, we're going to reach the stop. And what's going to happen? The tab's going to move even further, and that's help the pilot to move that control. Yeah. So the servo tab connected directly to pilot's controls in the cabin. Yeah. Less effort to move the tab than move the whole surface. Elevators can be moved not only directly by the control column, but also by the servo tab on the trailing edge, depending on the speed of the aircraft. Low speeds, large deflection of the elevator is required. Pawl on the follow-up crank reaches the stop. Pilot raises the elevator directly, so pilot moving. Pawl is that little lug there, hits the stop. That's going to move the elevator directly. Go the other way, pulls back. Yeah, that pawl's going to hit the stop and move the whole control surface. High speeds, aerodynamic loads are great. Small deflection of the elevators are required. The tab alone can move the elevator without the follow-up crank making contact. Yeah, so as he moves the elevator at higher speeds, yeah, the whole thing's not swinging, but the connection to the tab is moving the servo tab, and that in turn is moving the elevator for us. Spring tabs, yeah. Form of aerodynamic balance, we said that yesterday, assists the pilot in moving the control surface at high speeds only. Low speeds, the tab remains in the neutral position. Spring tabs fitted on any control surface. This one's showing it on an aileron. Differential aileron sector transfers the movement of the aileron cables to the spring tab. Yeah, so that the cables are moving via the quadrant. We're getting the input to the tab. Tab unit has touched the front spar of the aileron. Push-pull rods connect the balance lever to the differential sector. Yeah. Aileron operated at low speed. The torsion bar holds the balance lever in the central position. The spring tab remains in, it says in continuation, just remains in line with the elevator. So at low speeds, the torsion bar is moving, and the torsion bar is moving the whole aileron. Yeah, high speeds, the force necessary to move the aileron causes that torsion bar to twist, and the twisting of the torsion bar causes the spring tab to move in relation to the aileron, decreasing the force required to move it. Yeah, so the more air load on the aileron, the more spring tab you get to help him. However, there is a stop in there limiting the amount of movement we're going to get. So that's your spring tab, that torsion bar, just a twisting bar. Slow speeds, yeah, no real load. The whole aileron's going to move. The spring tab will remain in flush with it. Yeah, the higher the speed now, the more resistance. That torsion bar will twist. It'll kick in, and that will allow the tab to move proportionally to the aileron as we're moving the control column.
Jim,
yeah.
This spring tab is used in high speed or low speed?
The spring tab can be used in either, but mainly at high speeds. It depends on the way it's set up. Yeah, with it, I don't want to confuse the issue. So normally it'll be at high speed to assist the pilot to move the control at higher speeds. If it's on the rudder, yeah, it can be fitted the other way around. So the faster the aircraft's going, the spring tab can be used as an anti-balance tab. So the faster they're going, the less movement you want on the rudder. So we can use a spring tab to make it harder for the pilot to move the rudder.
Like in the book one, we studied earlier, I think yesterday. There's a direct control. There is a direct control at slow speed, and servo tab control at higher speed is mentioned. Spring tab are placed in the control system so that at low speed the pilot will have a direct control in moving the main control surface. It's a little bit confusing, contradicting between this. In the book one, there is saying that spring tab in low speed and servo tab is in high speed, but here is opposite, spring tab in the higher speed. This is the old book, page number 61. In book one, there is a spring tab, geared balance tab, and next one is the servo tab and spring tab. There is a mention.
So I haven't got that other book open at the minute. So it says a spring tab, aerodynamic balance, which assists the pilot move the control at high speed. So in book one, is it saying at low speed?
Yes.
Right. So let me make a note of that. So page 61.
68.
68, and that's in book one.
Yes, it's older one.
Old book, yeah. Or 67 in our notebook. Last line. The servo tab control at a higher speed.
That's last line. And the very first line there is mentioned springs are placed in the control system so that at low speed the pilot will
direct control.
Yeah. Just let me open the book so that right. So you're saying page 68.
67, I think.
You can just go with the heading spring tab.
Spring tabs, yeah. Right, spring tab, Yeah, springs are placed in the system so that at low speed, the pilot will have direct control moving the main control surface. No movement of the tab.
In the last sentence, there is mentioned direct control at slow speed and servo tab control at higher speed is mentioned.
Yeah. Yeah, so at slow speed, you've got full control over the control surface. Yeah. And at higher speed, the spring tab is going to control the surface for us. That's what that's trying to say. Yeah, so aerodynamic force on the tab produced terminated spring tab. Yeah, so that top line, springs are placed in the control system so that at low speed, the pilot will have direct control moving the main control surface. Yeah, you happy with that?
I just want to know, spring tab is used for slow speed or high speed?
The spring tab, yeah, is used to help the pilot at high speeds.
High speed?
Yeah. At low speeds, the spring tab is going to stay in line with the control surface. So he's got the full control surface movement. Yeah. So again, the example that we're seeing in book 2 that we're looking at now on page 51. Yeah, the aileron is operated at low speed. The torsion bar holds the lever in the central position, and the spring tab remains in continuation with the aileron, which is what it's saying in book 1 as well. Yeah, springs will stay in line with the control surface at low speeds. Yeah, and then at higher speeds, the tab will move to give the pilot the assistance to move the control.
It's mean the same, right?
Yeah. That's your control. Yeah. At low speeds, that tab is going to remain in the neutral position. It's going to remain in line with the control surface. At higher speeds, because of the way it's set up, yeah, at higher speeds, once we reach a higher speed, the spring will allow the tab to move as the control surface is being moved. So as the control surface is being moved, the tab will move to help the pilot to move that main control surface. Again, I don't want to confuse the issue, but with the rudder, we can actually have the spring tab working as an anti-balance tab when we get to a higher speed. Okay. Yeah. Has that sort of answered your question there?
Okay, Jim. The spring tab for
sure?
high speed, that's it, right?
Yeah, the spring tab, for what we're talking about, the spring tab, at low speeds, it'll stay in line with the trailing edge of the control surface. At high speeds, it will move to help the pilot to move that control.
That means no reaction for the low speed, right?
Yeah, low speed, it'll just stay in its neutral position.
Neutral position. Yeah. Okay. Thank you.
Okay with that?
Okay, Jim. Thank you.
My pleasure. Anybody else got anything before I move on? Everybody's being deliberately quiet now, aren't they? I lost my page now. Is everybody else okay with that? No problems, no queries, no questions? Spring tab, let's say that'll stay in line. At higher speeds, when the resistance on the aileron, it's going to cause that bar to twist, and it's the twisting of the bar that's going to move the spring tab.
Hello, Jim.
Yeah.
So this tab, this spring tab, as what I simply understood is, in low speed, the pilot can directly control the control surface from control column, but in high speed, when the pilot moves the control column, it moves the tab, and then tab moves the control surfaces.
That's the servo tab.
Yes.
Yeah.
And spring tab is same, I think.
Spring tab is a type of servo tab.
Yes.
Yeah.
But Jim, can you please...
with the servo tab, the servo tab is directly connected to the pilot's controls. The spring tab is connected to the control surface. But they're going to perform the same sort of function.
The spring tab is connected to the control surface. Servo tab is directly...
Yeah, the servo tab, where are we? Yeah, your servo tab, yeah, there's a direct connection from the control column to the tab. Yeah.
Okay. Okay.
So at low speeds with the servo tab, as the pilot's moving the control surface, yeah, everything's sweet. At higher speeds, what happens is the pilot's moving the controls, yeah, he's actually moving the tab. So rather than him moving the full control surface at higher speeds, all he's doing is moving the tab. And it's the movement of the tab that's moving the control surface. You with me?
Yes, yes.
So it's the tab that's doing the work, hence the name servo servant. Yeah. So the pilot's moving the controls. Yeah. Higher speeds, he's moving the tab before the stops move the full control. So he's got direct control over the tab, if you like. With the spring tab, the spring tab isn't connected directly to the pilot's controls. What's happening? The pilot is moving the, in this case, the aileron. Yeah, and at low speeds, he's got full control over the aileron. The faster he goes, the higher the speeds, the more resistance that aileron is going to get to because of the air loads acting on it. And that resistance of the air loads is going to cause this torsion bar to move, to twist. And it's the twisting of that torsion bar that's now going to move the spring tab. And the movement of the spring tab is going to give the pilot the aerodynamic assistance or the balance effect to move the control.
Okay, Jim, I got it. That in servo tab, the control column is directly connected to tab.
Yep.
But in spring tab, the control column is not directly connected to the tab, but it is connected to the control surface.
That's the one. Yep.
And during low speed, this spring tab directly controls the control surface, but in high speed, when the pilot moves the control column, it controls the tab because of that Trojan bar and core.
In the servo tab, yeah. Well, in the servo, yeah, when the pilot moves the control surface at high speeds, he is moving the tab, and it's the tab that's moving the control surface. Yeah. At high speeds, it's the resistance of the airflow on the main control that's causing the spring tab to move.
Okay, Jim. Anyway, so the difference between the main difference between this servo tab and servo spring tab is the connections from the control column to the to this. In servo tab, the the pilot's control is directly connected to the tab, but in spring servo tab, it is not directly connected to the tab. It is connected to the control surface.
Yeah, exactly. Bingo. Yeah.
Okay, thank you.
That's
Jim,
exactly.
can you again please describe this electrically operated trim system?
Yeah.
Yes, this schematic
that one.
diagram.
Yeah. All we've got. Forget the electrics just for a second. Yeah, we've got the trim wheel, and the trim wheel is mechanically connected to the trim jack by cables, by mechanical cables. What we can do is incorporate an electric motor, yeah? And by incorporating the electric motor, we've got electric switch on the thumb position on the control column. Yeah, so by pressing that electric switch, I'm sending a signal down to a little motor. That little motor is going to run, and it's going to via a cable and a pulley. All that's happening is that electric motor is moving in or out, and that's putting an input into the screw jack. Yeah.
Okay, Jim.
That way, it's a pretty shit drawing, that one. But basically, what we're trying to say is the control switch for whatever it is, the ailerons or the elevator or the rudder. If we're going to use an electric system, it's got to have two consecutive inputs into it. It's got to have an armed input and a control input before the electric motor will run. And that is prevent the motor from running to its full extent. If it did that, it would create a hazard, because the tab would go to its full range, and it make the aircraft quite difficult to control. So in the electric system, we've got to have the two inputs. We've got to have the armed input and the control input.
Okay, Jim. Okay, Jim.
Okay. You sure?
Sure, Jim. Sure. Thank you.
Anybody else got any questions before I run on? No. Right. I think we're nearly there, guys, for today. Push-pull tubes, yeah. Rather than using control cables, we can use push-pull tubes. Again, using torque tubes for converting linear to rotary motion, and bell cranks and push-pull tubes. We can operate our control surface. Yeah, and this typical one. Yeah, there's push-pull tubes. Again, lever, bell crank, control stops. Yeah, and your movement of your control surface. The advantages, the disadvantages are fairly self-explanatory. I won't dwell on those. It says less weight. We haven't got the complex. It says here it's greatly complicated, but it's more of a robust system. They're quite good. Don't apply loads to the structures. The tube's made out of same material as the aircraft, so you haven't got expansion, contraction, that sort of thing. Your tubes aren't going to stretch like a cable might. And we don't require any return runs, because the thing's push-pull. It's going in both directions. And again, there's a brief description. I wouldn't spend too much time worrying about push-pull tubes. Yeah, they're just a method of moving the control. Just remember that the primary stops on the push-pull tube system, the primary stops are at the control column, the secondary stops are at the control surface. If you remember those, then the control cable one's the opposite. Yeah, just example of your levers and your bell cranks. Yeah, support guides, and away we go. Right. Just let me down here a second. Yeah, we'll just do this bit on stall and then we'll call it a day, if that's all right. That'll take us nicely to a good place to start on Monday. Is everybody okay with that? Nobody okay with that?
Okay.
Okay, right.
Okay, Jim.
Okay, sir.
Stall. What are we doing when we stall the aeroplane then? What's happening when the aircraft stalls? Right. When we stall the aeroplane, we're going beyond the critical angle of attack. Yeah, the angle of attack is too large, and now the air that's trying to flow across is going to separate too early. Yeah, and we're not going to get enough lift to support the weight of the aircraft. So with a stall, it's a very, very dangerous condition to get into. So we need to give the pilot some sort of warning that he's approaching the stall condition. Yeah, so he's not going to get the aircraft to the point where it falls out of the air. How can he stall the aeroplane? Essentially, we're going up to the critical angle of attack. Two ways of doing that. He's going to pull the stick back too far, and he's going to be going too.
Catch that. Could you try again?
No, sod off. Who are you? I've got Siri joining in the lesson now. My phone has got a life of its own. Yeah, Siri's just saying, I didn't catch that.
I want to ask, what will be the question coming in exam from Siri?
Yeah. Yeah. Yeah, so pilots, if they're not watching what they're doing, there's a good possibility they could stall the aircraft. So the speed of the aircraft going too slowly, the angle of attack, the slower we go, the more we've got to increase the angle of attack. Yeah, so once we're approaching the stall condition, we need to give the pilot a bit of a warning. And the way we're going to do that is to put a stall warning computer into the aeroplane. And that stalling warning computer is going to be taking information from various points. Angle of attack sensors, or what they call alpha bands sometimes, stuck on the side of the fuselage, and they mimic the attitude of the aeroplane. Yeah, so as the angle of attack increases, the angle on the alpha vane or the angle of attack sensor increases, and once it gets to a certain point, it's going to tell the computer, the stall warning computer, and the stall warning computer is going to give the pilot some sort of warning. Yeah, so the angle of attack sensors, small aerodynamic vanes, live on the side of the aircraft. Vane positions the head of it says the rotor of a synchro. Basically, there's behind here, there's a little motor. As the angle of attack sensor increases, the little synchro behind there is sending a signal to the stall warning computer. Once we get to a certain point, the stall warning computer is going to flash up a warning in the cabin. Anti-icing, yes, we're going to have heaters in the stall warning vane, yeah, just so it don't freeze up. How we're going to warn the pilot? Yeah, well, we're going to give him whistles and bells. Yeah, we'll have an audio warning. Generally, there's going to be a flashing light as well. But one of the other ways that we can warn him is by a stick shaker. Yeah. So as we're approaching the stall, we'll give him a flashing light and maybe give him an audio warning. If he still continues towards the full point of stall, what happens is a little stick shaker starts going, and that's going to vibrate the stick backwards and forwards, and it's the action of the stick going backwards and forwards should alert him to the fact that he's nearly in the stall condition. From there, if he doesn't take any recovery action, then there's an automatic stall recovery system that will push the stick forward and bring the nose of the aircraft down. As the nose of the aircraft comes down, we're coming away from that stall condition. Yeah. Right, midway down page 57, yeah, the stall warning system is designed to operate at a speed 5% above the stalling speed for a particular aircraft configuration. What you've got to remember is we can fly at lower speeds if we put the flaps and the slats down. Yeah. So the stall warning system, the stall computer, is looking at the position of the flaps and the slats along with other things, but it's looking at the flap and slat position so that it's not giving him a warning unnecessarily. Yeah, so if let's say he's flying along, his stall speed is 110 knots or 100 knots, yeah, that's when he's going to stall. The warning system will give him a warning at 105 knots. If his stall speed is 80 knots with the flaps and slats down, the stall warning will give him whatever 5%, 84 knots, won't it? It'll give him a warning. So 5% above the stalling speed for a particular configuration, the warning will go off. Yeah. If he doesn't take any action, the stick shaker going off, if he ignores that, then the stick pusher will automatically push the nose of the aircraft down. Speed of the aircraft is going to increase because the nose has come down, and away we go. Large transport aircraft, duplicated stall warning and recovery. Yeah, so if either system detects a stall condition, it'll vibrate the column. Yeah. As both columns are joined together, obviously both columns are going to shake. Should operate at the same time. Warning lights will tell him that the stall warning system's operated. Also, they'll tell him which one should be switched off if we've got a false operation. So it's got its own little monitoring system in there as well. Yeah. System deactivated on the ground by the WOW switches because because we're going slowly on the ground. Yeah, we don't want the stall warning constantly going off. It'd be quite disruptive. So the stall warning system works through the WOW switches. And that's again on page 57. So your alpha vane, yeah, your airflow sensor on the side of the aircraft, mimicking the attitude of the aircraft. Yeah. If we get a stall warning, yeah, it'll give us a visual warning. If we get a fault in the system, again, it'll give us an indication. Individual systems, yeah, if we've got a fault in one of them, we can inhibit that system, podge the button, yeah, and again, the indication in this example, if the stall prevention has gone off, it'll give us a light to let us know. Flapper-ons. Yeah. Typical system then. Stall warning computer receives the angle of attack data from the alpha vane, operates the stick shaker at preset angle. Depending on the flap and slap position, depends when that kicks in. Stick pusher, low pressure air reservoir, or you could have an electric system. Yeah. Won't go too deep into the example it's giving. We don't need to worry about that. So we can have a pneumatic system or an electric system. The stick shaker is just a little motor on the back of the control column. And that little motor drives an eccentric weight. So as the weight goes round, where are we? Yeah, if that's the motor, yeah, attached to the motor there's a weight, yeah. So as that motor's turning, it's trying to turn this weight, and because the weight's offset, it's gonna vibrate as it goes round. As it's vibrating as it goes round, it's going to set up that shaking in the stick. Yeah, so stick shaker will go off. Yeah, pilot ignores it for whatever reason. He might be, I don't know, having a cup of tea or looking at the neighbour or whatever. If he ignores it, then the aircraft recovery system is going to kick in. And what happens with that is either an electric or a pneumatic system is going to be activated, and that's going to push the stick forward. And by pushing the stick forward, the nose of the aircraft is going to be brought down. Obviously, as the nose of the aircraft comes down, we're going to gather speed. As we gather speed, then we're coming away from the stall condition. Duplicated system, yeah. So if you've got one inhibited for whatever reason, the other one's still going to activate the system, protect it should it need to. If everything's fat, dumb, and happy, if one stick shaker goes off, because the systems are interconnected, both of them all work. Yeah. Stick shakers operate. Yeah. Nothing happens, then the system will send, in this case, compressed air from the bleed air system into a little actuator. The actuator will retract. As it pulls back, it's going to move the stick forward. Stick forward, away we go. Duplicated cable runs connect the pneumatic ram to the control columns. If engine bleed air is lost, there's a reservoir in the system that can do the job for us. Yeah, so you've got your reservoir, you've got your control valves. Yeah, via the control valves, we're allowing air to the pneumatic actuator. Pneumatic actuator retracts, it's going to pull the stick down with it. Yeah, and the other bit's just showing us the other half of the system, bleed air coming in. Yeah, bleed air topping up the reservoir. Your relief valve in the system, should you need it. Your which system's operating, and so on and so forth. We needn't worry too much about that. Yeah. Relief valve there to protect from overpressure, annunciators on the flight deck, telling us the condition of the system, low air pressure, stall valve open, stall valve B open, once they've operated. CWP indications to tell us there's a fault, should that be necessary. And then there's a couple of dozen pictures. Yeah, what's going on? The stall warning computer. What's it looking at? It's looking at the inputs from the alpha vane, the angle of attack sensor. It's looking at the position of the flaps and the slats. It's looking to see whether the wow switches are made or not. It's looking at the flap slat symmetry. Yeah. Taking in info from the air computer, the digital air data computer, looking at the engine, the throttle positions, yeah, and there's a test facility should we need it. So the stall warning computer's taking all that information in, analysing that information, and if it needs to, it's going to send a signal up to the stick shaker, and at the same time we'll get the audio warning normally. The electric operated one, same sort of thing. All we've got is a little motor, yeah, and that motor is putting an input into a quadrant, which in turn is going to move the stick forward to bring the nose of the aircraft down in the event of us approaching the stall condition. Yeah, so cable pusher, yeah, stick pusher, electric motor moving the quadrant, which in turn is moving the stick, and that, guys, takes us to where we need to be for this week. I've missed nothing. I've pointed out the bits that we need to highlight so far. We've been through the high-speed flight. What I would recommend sometime over the weekend, just for clarity, for your own peace of mind, just to make sure that you followed what I was saying, just have a look at that YouTube clip. It's about 20 minutes, if that, I think, and it just explains the supersonic flight quite nicely. Yeah, and it does explain the expansion wave, the oblique shock, the normal shock, and it just clarifies what's going on in high-speed flight. Yeah, that's I think we're five minutes ahead of track. So before we call it a weekend, has anybody got any questions whatsoever on what we've covered this week? No? Right, well, have a good weekend. Don't spend all your weekend reading books, but have a quick look through, and if there's anything you need clarifying, again, we can do that first thing on Monday. So if nobody's got anything for me, I shall bid you farewell for the weekend. Have a good weekend. Enjoy yourselves. And I'll see you at the usual time on Monday.
Okay, thank you, Jim.
Okay, thank you.
You also.
Dhanyavad.
Thank you, Jim. Dhanyavad.
Dhanyavad.
Thank you, Jim.
Dhanyavad.
Thank you.
Okay, cheers. Dhanyavad.
Dhanyavad.